Welcome to the ultimate guide on building a Dyson Sphere, one of the most ambitious and mind-boggling megastructures ever conceived by humanity. Imagine harnessing the energy of an entire star, powering civilizations for eons, and pushing the boundaries of what's possible in our universe. Today, we're diving deep into every aspect of this colossal endeavor, from the theoretical foundations to the practical steps needed to turn this science fiction dream into reality. The concept of a Dyson Sphere has fascinated scientists, engineers, and futurists for decades. First proposed by the visionary physicist Freeman Dyson in 1960, this idea challenges our understanding of energy, space, and the future of human civilization. But what exactly is a Dyson Sphere, and why would we ever consider building one? A Dyson Sphere is a megastructure that completely surrounds a star, capturing nearly all of its energy output. This energy could then be used to power advanced technologies, interstellar travel, or even entire planets. The potential applications are as limitless as the energy supply itself. But building such a structure is no small feat. It requires overcoming massive engineering, material, and logistical challenges. Before we dive into the how, let's take a moment to explore the why. Why should humanity aim to build a Dyson Sphere? The answer lies in the future needs of an advanced civilization. As our technological capabilities grow, so does our energy consumption. A Dyson Sphere offers a solution to the inevitable energy crisis, providing a nearly infinite supply of power that could sustain civilizations for millions of years. But before we can start construction, we need a solid understanding of the theoretical foundations. This means understanding the physics of stellar energy, the principles of megastructure design, and the material requirements for building something on such a colossal scale. We'll explore these concepts in detail, laying the groundwork for the more practical aspects of Dyson Sphere construction. One of the first decisions we'll need to make is choosing the right star. Not all stars are created equal when it comes to building a Dyson Sphere. Factors like the star's size, energy output, and stability play crucial roles in determining the feasibility of the project. We'll discuss how to select the ideal star for your Dyson Sphere and what makes some stars more suitable than others. Material science and engineering are at the heart of any large-scale construction project, and a Dyson Sphere is no exception. The materials used must withstand the harsh conditions of space, be incredibly strong, and, ideally, be sourced from within the solar system to minimize transportation costs. We'll cover the latest advancements in materials science that could make this project possible, including the potential use of nanotechnology and advanced alloys. Once the materials are secured, the next step is figuring out how to actually collect and transmit the energy. This involves choosing the right method for energy collection, such as photovoltaic panels or other advanced technologies, and deciding how to transmit that energy back to Earth or other locations. We'll explore the options and discuss the efficiency and practicality of each method. The construction process itself is another monumental challenge. Building a Dyson Sphere requires innovative techniques, likely involving autonomous robotic systems, modular construction methods, and sophisticated orbital assembly strategies. We'll delve into these techniques and explore how to avoid potential pitfalls, such as collisions or structural failures. As we explore these topics, we'll also compare different approaches to building a Dyson Sphere, such as the Dyson Swarm versus the Dyson Shell. Each has its own advantages and disadvantages, and the choice between them will depend on factors like available resources, desired outcomes, and long-term goals for the structure. So, let's get started on this journey to the stars, where we'll explore the intricacies of building a Dyson Sphere, a project that could redefine the future of energy, technology, and human civilization. Whether you're a science enthusiast, an aspiring engineer, or just curious about the future, this guide has something for you. To fully grasp the potential of a Dyson Sphere, we must first understand the nature of stellar energy. Stars are essentially colossal fusion reactors, constantly converting hydrogen into helium and releasing immense amounts of energy in the process. This energy radiates outward in all directions, a vast and untapped power source just waiting to be harnessed. The energy output of a star is determined by its mass and composition. Larger stars burn hotter and faster, producing more energy, but they also have shorter lifespans. On the other hand, smaller stars like red dwarfs burn steadily for billions of years, providing a more consistent energy supply over time. Harnessing this energy requires capturing as much of the star's output as possible. A Dyson Sphere's design must account for the intensity of the radiation, which varies across different wavelengths. From visible light to infrared and ultraviolet, each type of radiation offers unique opportunities and challenges for energy collection. The sheer scale of energy produced by even a modest star is staggering. For example, our Sun emits about 3.8 x 1026 watts of power. Capturing even a fraction of this energy could power entire civilizations, making the construction of a Dyson Sphere an incredibly attractive proposition for future technological advancements. However, not all of this energy can be easily collected. Some of it is lost to space, and the efficiency of energy capture depends heavily on the technology used. Advanced photovoltaic materials, for instance, could convert a significant portion of this energy into usable power, but they must be capable of withstanding the harsh environment near a star. Another critical factor is the star's life cycle. Stars evolve over time, changing in size, temperature, and energy output. A Dyson Sphere must be designed with these changes in mind, ensuring it remains functional and stable throughout the star's life. Understanding stellar life cycles is therefore crucial for the long-term success of the project. The balance between energy output and stellar stability is a delicate one. High-energy stars offer more power, but come with greater risks, such as solar flares and eventual supernovae. Low-energy stars provide longevity, but at the cost of lower power levels. The design and material choices for a Dyson Sphere will need to reflect these trade-offs. Stellar energy is not evenly distributed. It fluctuates due to various factors, including magnetic activity and rotational dynamics. These fluctuations can affect the consistency of energy collection, necessitating adaptable systems within the Dyson Sphere that can respond to these changes in real time. This adaptability is key to maintaining a steady energy supply. Moreover, the distance of the Dyson Sphere from the star is a crucial consideration. Too close, and the structure could be overwhelmed by intense radiation and heat. Too far, and the efficiency of energy collection drops significantly. The optimal distance must strike a balance between maximizing energy capture and ensuring the structure's integrity. Radiation pressure from the star also poses a challenge. This force, although small, can impact the stability of components within a Dyson Sphere, especially in a Dyson swarm configuration. Understanding and mitigating these forces through precise engineering is vital for the structure's stability over time. The energy collected by a Dyson Sphere must also be managed efficiently. Without proper systems in place, the enormous amounts of power could be wasted or even become hazardous. Energy storage, transmission, and conversion systems will need to be incredibly advanced to handle the scale of power involved. There's also the consideration of waste heat. A Dyson Sphere will absorb not just light, but heat as well. This heat must be dissipated to avoid damaging the structure and to maintain a stable environment for energy conversion. Effective thermal management strategies will be a key aspect of any successful Dyson Sphere design. Another aspect to consider is the interaction of the Dyson Sphere with the star's magnetic field. Stars generate powerful magnetic fields that can influence the operation of electrical systems within the sphere. Shielding and grounding technologies must be incorporated into the design to protect the sphere's infrastructure from these magnetic effects. Furthermore, the impact of the Dyson Sphere on the star itself cannot be ignored. While the sphere captures energy, it might also alter the star's dynamics in unforeseen ways. Careful monitoring and adaptive strategies will be necessary to ensure that the star remains stable throughout the sphere's operation. Lastly, we must consider the long-term sustainability of the Dyson Sphere. As the star evolves, the sphere must adapt, or risk becoming obsolete. Continuous advancements in materials, energy management, and structural design will be essential to keep the Dyson Sphere functional over the immense timescales involved. Understanding stellar energy in all its complexity is the foundation upon which the entire concept of a Dyson Sphere is built. It's only by mastering this knowledge that we can hope to move forward with the practical steps of designing and constructing such a transformative structure. Megastructures represent some of the most ambitious ideas ever conceived by humanity. They push the boundaries of engineering and physics, challenging us to rethink what's possible on a cosmic scale. A Dyson Sphere is one such megastructure, but it's only one part of a much broader category of colossal engineering feats. These structures are defined by their enormous size and the unprecedented technical challenges they present. They often require the utilization of resources and energy on a scale far beyond what we currently possess. However, the potential benefits of these structures are equally vast, promising to reshape civilizations and even entire ecosystems. Building a megastructure means dealing with issues of stability and durability on a level we've never encountered before. Traditional engineering principles need to be adapted or completely reimagined to cope with the sheer mass and forces at play. The structural integrity of a megastructure is paramount, as even minor failures could lead to catastrophic consequences. In designing a megastructure, we must consider not just the materials and methods used, but also the environment in which it will exist. Space, with its vacuum, radiation, and microgravity, offers unique challenges that differ greatly from terrestrial construction. The absence of a protective atmosphere means that these structures must be incredibly resilient against both natural and artificial threats. The concept of a megastructure also raises questions about energy management. These structures often require massive amounts of energy to maintain and operate, far beyond the capabilities of current technology. In many cases, the energy source becomes an integral part of the design itself, as with a Dyson Sphere, which both harvests and depends on the energy of a star. One of the most fascinating aspects of megastructures is their potential for scalability. Unlike smaller structures, megastructures can often be expanded or adapted over time, growing to meet the changing needs of the civilization that built them. This scalability makes them not just impressive feats of engineering, but dynamic and evolving components of a society's infrastructure. The sheer size of megastructures also impacts their construction timeline. These are projects that can take centuries or even millennia to complete. This long-term perspective requires a commitment to a vision that spans generations, with each phase of construction building upon the last in a carefully coordinated sequence. However, the construction of a megastructure is not just about physical labor and materials. It also involves complex logistical planning, the coordination of vast resources, and the management of thousands, if not millions, of workers and autonomous systems. The scale of these operations is as unprecedented as the structures themselves. Megastructures also have the potential to alter the very fabric of space around them. Their massive presence can impact gravitational fields, influence nearby celestial bodies, and even affect the flow of time, depending on their mass and speed. These effects must be carefully calculated and managed to avoid unintended consequences. In addition to their physical presence, megastructures often serve symbolic purposes, representing the pinnacle of a civilization's technological and cultural achievements. They stand as monuments to human ingenuity and ambition, reflecting our desire to shape and control our environment on the grandest scale possible. The design process for a megastructure requires collaboration across multiple disciplines, from physics and engineering to environmental science and sociology. Each aspect of the structure must be meticulously planned and executed, with input from experts in various fields, to ensure that the final product is both functional and sustainable. Moreover, the construction of megastructures raises important ethical questions. The resources required for such projects are immense, often necessitating the exploitation of entire planets or asteroid belts. This brings up issues of environmental impact, resource allocation, and the potential for conflict over the control of these vital materials. Communication is another crucial aspect of managing a megastructure. The vast distances involved in space construction mean that traditional methods of communication may be too slow or unreliable. Advanced communication systems, possibly even quantum-based technologies, will be essential for coordinating the complex activities involved in these projects. Furthermore, the maintenance and repair of a megastructure pose unique challenges. These structures are so large that regular maintenance could involve the efforts of entire fleets of spacecraft or autonomous drones, constantly monitoring and repairing sections of the structure to ensure its continued operation. Finally, the concept of a megastructure is not just a technical challenge, but a cultural one as well. It represents a shift in how we view our place in the universe, pushing us to consider what we are capable of as a species and what responsibilities come with that power. The creation of a megastructure is as much about vision and purpose as it is about steel and energy. Calculating the energy output of a star is a fundamental step in the design of a Dyson Sphere. This calculation starts with understanding the star's luminosity, which is the total amount of energy it emits per second. Luminosity depends on the star's mass, temperature, and radius, all of which influence how much power we can potentially capture. To determine how much energy can be harvested, we first need to calculate the surface area of the Dyson Sphere, or swarm, that will surround the star. The energy intercepted by this surface is directly related to the star's luminosity, with larger surface areas capturing more energy. This relationship drives the scale of the entire project. However, not all the intercepted energy will be usable. The efficiency of the energy conversion systems, such as photovoltaic panels or other technologies, plays a critical role in determining the actual amount of power that can be harnessed. These efficiencies must be factored into the calculations to provide a realistic estimate of the energy output. Another important factor is the distance of the Dyson Sphere from the star. As the distance increases, the energy density decreases, meaning less power is available per square meter of the sphere's surface. Finding the optimal distance where energy capture is maximized without compromising the structure's stability is crucial. In addition to these basic calculations, we must account for energy losses due to various factors, including radiation pressure, thermal losses, and potential energy dissipation through the structure itself. These losses can significantly reduce the net energy output, so they must be carefully quantified and minimized. For stars with variable output, such as those experiencing solar flares or cycles of increased activity, energy output calculations must also include a margin of safety. This ensures that the Dyson Sphere can handle peak outputs without being damaged or overloaded, maintaining consistent energy production even under fluctuating conditions. The star's spectrum also affects energy output calculations. Different wavelengths of light carry different amounts of energy, and the Dyson Sphere must be optimized to capture as much of this energy as possible across the entire spectrum. This involves selecting materials and technologies that can efficiently convert a broad range of wavelengths into usable power. Calculating the potential energy output also requires us to consider the long-term evolution of the star. As the star ages, its energy output will change, potentially increasing or decreasing, depending on its mass and type. A successful Dyson Sphere must be designed to adapt to these changes, ensuring a consistent energy supply over millennia. Moreover, the scale of the energy output is so vast that it demands new ways of thinking about energy storage and distribution. Traditional methods are insufficient for handling the immense power generated by a Dyson Sphere, necessitating the development of advanced storage solutions capable of managing this unprecedented energy flow. These calculations also influence the economic feasibility of the project. The total energy output determines the potential return on investment, helping to justify the massive resources and time required for construction. Accurate energy calculations are therefore essential for securing the funding and support needed to bring the project to fruition. In addition to practical considerations, energy output calculations also have implications for the broader universe. A Dyson Sphere would significantly alter the energy dynamics of its star, potentially affecting nearby celestial bodies, or even detectable from other star systems. Understanding these broader effects is part of the responsibility of harnessing such a powerful resource. Another consideration is the potential for energy redistribution. The captured energy could be used not just for local consumption, but also for powering spacecraft, other planets, or even interstellar communication. The calculations must account for how energy will be divided and transmitted across different uses and locations. Advanced simulations and models are crucial tools in refining these energy output calculations. They allow us to test different scenarios, optimize the design, and predict how the Dyson Sphere will perform under various conditions. These simulations are invaluable in reducing the risks associated with such a complex and ambitious project. As we calculate energy output, we must also consider the impact on future technological developments. The energy generated by a Dyson Sphere could drive breakthroughs in fields like artificial intelligence, quantum computing, and even space travel, making accurate predictions about energy output essential for planning these advancements. Ultimately, energy output calculations are about more than just numbers. They are about unlocking the future. By accurately assessing the potential power of a Dyson Sphere, we lay the foundation for a new era of technological and societal evolution, powered by the energy of the stars themselves. Building a Dyson Sphere demands materials that can withstand the harsh environment of space while maintaining structural integrity over potentially thousands of years. The challenge begins with identifying substances that are both strong enough to endure constant solar radiation and light enough to be launched and assembled in orbit. This balancing act between strength and weight is one of the key challenges in material selection. One of the most promising materials for such a megastructure is carbon nanotubes. Known for their incredible tensile strength and lightweight properties, carbon nanotubes could form the backbone of the Dyson Sphere's structure. However, manufacturing and assembling these materials on a scale required for a Dyson Sphere remains a significant technical hurdle. Beyond the physical strength, the materials must also be resistant to the intense heat and radiation emitted by the star. Traditional materials would degrade rapidly under such conditions, so advanced composites or novel alloys may be necessary to ensure longevity. Research into materials that can reflect or absorb high levels of radiation without breaking down is critical. The vast quantities of materials required also present logistical challenges. A Dyson Sphere would need more raw materials than could be feasibly transported from Earth, necessitating in situ resource utilization. This means mining asteroids, moons, or even planets within the star's system to obtain the necessary building blocks. Mining these celestial bodies comes with its own set of challenges. The process requires not just the extraction of raw materials, but also refining them in space, which involves developing technologies that can operate effectively in low-gravity and vacuum environments. These operations need to be highly efficient to minimize waste and energy consumption. Transportation of materials from mining sites to the construction site of the Dyson Sphere is another obstacle. Moving vast amounts of material across space requires propulsion systems that are both powerful and economical. Solar sails or electromagnetic propulsion systems might offer solutions, but their development is still in the experimental stages. Once the materials are gathered and transported, assembling them into a coherent structure presents another layer of difficulty. Traditional construction methods are impractical in the vacuum of space, so robotic and automated systems will likely play a crucial role. These systems must be incredibly precise to ensure that the structure remains stable and functional. Material fatigue is also a concern. Over time, even the most durable materials will degrade under constant exposure to the elements of space, such as micrometeoroid impacts and thermal cycling. Regular maintenance and potential material replacement plans will need to be part of the long-term strategy for sustaining the Dyson Sphere. Another challenge is the sheer scale of the material required. The Dyson Sphere will need to cover an area far greater than any structure ever built, requiring an almost unimaginable amount of material. Efficient use of these materials, through innovative design and construction techniques, will be essential to keep the project within feasible limits. The cost of these materials, both in terms of economic resources and energy expenditure, is another major factor. Even with in situ resource utilization, the energy costs associated with extracting, refining, and transporting these materials are astronomical. Ensuring that the Dyson Sphere can generate enough energy to justify these costs is a fundamental part of the project's planning. Beyond the immediate technical challenges, there are also issues related to material sustainability. The long-term success of a Dyson Sphere depends on the ability to repair and replace materials as needed, which means ensuring a steady supply of resources over potentially thousands of years. This requires planning for sustainability from the very beginning. The potential environmental impact of harvesting these materials from other celestial bodies must also be considered. Mining operations on a massive scale could disrupt ecosystems or even destabilize the bodies being mined. Ethical considerations must be balanced with the technical and economic aspects of the project. Furthermore, the choice of materials will also influence the overall design and function of the Dyson Sphere. Different materials may allow for different structural configurations or energy collection methods, making material selection a critical decision that affects every aspect of the project. This interdependence between materials and design adds complexity to the planning process. Advances in materials science will play a crucial role in overcoming these challenges. Ongoing research into new materials, such as metamaterials or self-repairing materials, could provide the breakthroughs needed to make a Dyson Sphere feasible. These innovations may also lead to unexpected benefits in other areas of technology. In the end, the material requirements and challenges are not just about overcoming physical obstacles. They also push the boundaries of what humanity can achieve, driving technological progress and expanding our understanding of the universe. The solutions we develop in pursuit of a Dyson Sphere could reshape our capabilities in space exploration, engineering, and beyond. Creating a stable orbital structure around a star is one of the most complex challenges in constructing a Dyson Sphere. The structure must maintain its position relative to the star, avoiding collisions and ensuring that its components remain in a precise and stable orbit. Understanding the physics of orbital mechanics is essential to achieve this balance. Orbital stability is governed by the gravitational pull of the star, which keeps the structure in orbit, and the centrifugal force generated by the structure's motion. These forces must be carefully balanced to prevent the structure from drifting too close to the star or being flung into space. Any imbalance could result in catastrophic failure. For a Dyson Sphere, especially in the form of a Dyson swarm, each individual component must maintain a stable orbit without interfering with the orbits of others. This requires precise calculations and positioning, ensuring that all components follow paths that avoid collisions while maximizing energy collection. The complexity of this task increases with the number of components involved. The shape and distribution of the Dyson Sphere's components play a crucial role in maintaining orbital stability. A perfect spherical distribution is theoretically possible, but it requires precise control over the speed and trajectory of each segment. Any deviation from the ideal shape could lead to gravitational perturbations that destabilize the structure. In some designs, a Dyson ring or partial Dyson sphere is considered to simplify the problem of orbital stability. By concentrating the structure along a specific orbital plane, the forces involved are easier to manage. However, this approach limits the amount of energy that can be captured and may not be suitable for all purposes. Additionally, the orbital speed of the structure must be carefully controlled. Components that orbit too slowly will spiral inward toward the star, while those that move too quickly risk escaping into space. Maintaining the correct orbital velocity is critical for the long-term stability of the Dyson Sphere. Interactions between different segments of the Dyson Sphere also need to be considered. Gravitational forces between the components can cause shifts in their orbits over time, leading to potential collisions or the gradual drift of the structure out of its optimal position. These interactions require continuous monitoring and adjustment. In some proposed designs, active stabilization systems are included to correct for any deviations in orbit. These systems might use small thrusters, electromagnetic forces, or other technologies to keep each component of the Dyson Sphere in its proper place. The energy cost of these systems must be factored into the overall design. Moreover, the star's own activity can influence the stability of the Dyson Sphere. Variations in solar radiation, flares, and magnetic activity can all exert forces on the structure, potentially disrupting its orbit. The design must account for these variations, incorporating flexibility and resilience into the structure's positioning. The construction process itself poses additional challenges for maintaining stable orbits. As new segments are added, the gravitational balance of the system changes, requiring constant recalibration of the orbits. This dynamic process must be carefully managed to prevent instability during the construction phase. Long-term stability also depends on the predictability of the star's behavior over millennia. Stars gradually lose mass as they burn fuel, which can alter the gravitational pull on the Dyson Sphere. Predicting these changes and designing the structure to adapt to them is essential for ensuring that the Dyson Sphere remains stable over its intended lifespan. To maintain the structural integrity of the Dyson Sphere, it's important to minimize vibrations and oscillations that can occur as a result of gravitational forces and external influences. These vibrations can lead to structural fatigue and eventual failure if not properly controlled. Damping mechanisms or flexible design elements may be necessary to absorb and dissipate these forces. The positioning of the Dyson Sphere relative to other celestial bodies in the system also needs consideration. The gravitational influence of planets, moons, or even passing asteroids could perturb the orbits of the structure's components. The design must ensure that these influences are either mitigated or accounted for in the structure's orbital path. Finally, the scale of the Dyson Sphere amplifies all these challenges. The sheer size of the structure means that even small errors in the initial placement or subsequent adjustments can have massive consequences. Achieving and maintaining stable orbits for the entire system requires precision on an unprecedented scale. Understanding the physics of stable orbital structures is not just a technical requirement, but a fundamental part of making the Dyson Sphere a reality. It's the key to unlocking a future where humanity can harness the power of a star, expanding our reach and capabilities beyond anything we've imagined before. Selecting the right star is a critical decision in the construction of a Dyson Sphere. The star's characteristics will dictate the structure's design, energy output, and long-term viability. Not every star is suitable, so careful consideration is needed to ensure the chosen star meets all necessary criteria. The first criterion to consider is the star's mass. A star with too much mass may burn too hot and too quickly, shortening the lifespan of the Dyson Sphere. Conversely, a star with too little mass may not provide sufficient energy to justify the immense effort required to build the structure. Stellar stability is another key factor. The star should have a relatively calm and predictable activity, with minimal solar flares and other disruptive events. A stable star ensures that the Dyson Sphere can operate without constant adjustments or risks of damage from sudden energy spikes. The star's lifespan also plays a crucial role. Ideally, the star should have a long, steady life ahead of it, allowing the Dyson Sphere to function for millennia. Red dwarf stars, for example, are known for their longevity, making them appealing candidates for long-term projects. Another important consideration is the star's spectral type. Different types of stars emit different wavelengths of light, which affects the design of the energy collection systems. A star that emits a broad spectrum, including significant amounts of visible and infrared light, is generally more desirable for maximizing energy capture. Proximity to Earth or other inhabited systems is also a factor. While a nearby star may seem convenient, it's essential to balance distance with other criteria. A closer star reduces communication delays and transportation costs, but may come with higher risks due to its influence on the surrounding space environment. The presence of other celestial bodies in the star's system must be considered as well. A star with multiple planets, moons, or asteroid belts could complicate the construction and operation of the Dyson Sphere. These bodies might introduce gravitational influences that could destabilize the structure or create obstacles during construction. The star's rotational speed is another factor that can impact the design of the Dyson Sphere. A rapidly rotating star might introduce additional forces that need to be managed, complicating the overall stability of the structure. A more slowly rotating star typically offers a more stable environment for the Dyson Sphere. Magnetic activity is yet another criterion. Stars with strong magnetic fields can interfere with the electronics and energy transmission systems of the Dyson Sphere. Selecting a star with minimal magnetic disturbances helps to ensure the smooth operation of the structure over time. The chemical composition of the star can also influence its suitability. Stars rich in heavy elements may offer more potential for resource utilization within the system, but they might also have more complex behaviors that need to be managed. Understanding the star's composition helps to predict its future evolution and any potential challenges. The star's age is important too. Younger stars may still be in a phase of significant change, making them less predictable and stable. Older stars, nearing the end of their life cycle, might not offer the longevity required for such a massive project. The ideal candidate would be a star in the stable, middle phase of its life. Additionally, the star's energy output relative to its size must be considered. Some stars are more efficient at converting their mass into energy, making them more attractive targets for a Dyson Sphere. The more energy a star can provide over its lifetime, the more viable the Dyson Sphere becomes as a long-term energy solution. Potential for future expansion is another aspect to consider. The star should offer the possibility of scaling up the Dyson Sphere, or adding additional structures in the future. This potential ensures that the initial investment can continue to yield benefits as technology and needs evolve. Lastly, the impact of the Dyson Sphere on the star itself should not be overlooked. The structure could alter the star's behavior over time, potentially accelerating its evolution or changing its energy output. Understanding these potential effects is crucial to ensure that the star remains a viable energy source throughout the Dyson Sphere's operational lifespan. G-type stars, like our Sun, offer a balanced mix of stability and energy output, making them prime candidates for Dyson Sphere construction. Their relatively long lifespans provide a consistent energy source, while their radiation spectrum is ideal for most energy-harvesting technologies. These stars are abundant in our galaxy, offering many potential targets. One major advantage of G-type stars is their moderate mass, which leads to a stable fusion process. This stability reduces the likelihood of unpredictable solar events that could disrupt the Dyson Sphere's operation. Additionally, their energy output is sufficient to power advanced civilizations, providing the high levels of energy needed for large-scale technological infrastructure. Red dwarfs, on the other hand, are the most common type of star in the universe, and they have extremely long lifespans, often lasting trillions of years. This longevity makes them attractive for projects that require a stable energy source over incredibly long timescales. A Dyson Sphere around a red dwarf could potentially operate for an unimaginably long duration. The lower energy output of red dwarfs compared to G-type stars means that the Dyson Sphere would need to be closer to the star to capture adequate energy. However, this closer proximity simplifies the design and reduces the overall size of the structure. The reduced energy output also means less stress on the materials used in construction. And red dwarfs also have the advantage of being less prone to extreme solar flares than larger stars. This makes them safer candidates for Dyson Spheres, as the risk of sudden massive energy releases that could damage the structure is lower. The calm nature of red dwarfs offers a more predictable environment for long-term projects. Another benefit of red dwarfs is their slow fusion rate, which contributes to their longevity. This slow burning allows for a more controlled and sustained energy output, which can be more manageable for energy collection systems. The consistency of energy production over time is a significant advantage for maintaining stable operations. G-type stars, despite their shorter lifespans compared to red dwarfs, still offer significant advantages due to their higher energy output. This allows for the generation of more power in a shorter time frame, which can be crucial for rapidly expanding civilizations. The increased energy availability can accelerate technological advancement and expansion. The radiation spectrum of G-type stars is particularly well suited to current photovoltaic technologies. The peak emission in the visible spectrum aligns well with the capabilities of most solar energy collection systems. This compatibility reduces the need for specialized technology, making G-type stars a practical choice for Dyson Sphere construction. Red dwarfs, although cooler and dimmer, emit most of their energy in the infrared spectrum. This requires specialized energy collection systems designed to harness infrared radiation efficiently. While this adds complexity to the Dyson Sphere's design, it also opens the door to the development of new technologies specifically tailored for infrared energy capture. The smaller size of red dwarfs also means that a Dyson Sphere could be constructed with less material, reducing the overall cost and resource requirements. This smaller scale makes red dwarfs more accessible targets, especially for civilizations in the early stages of building megastructures. The reduced material needs could lower the barrier to entry for such projects. G-type stars offer the benefit of a balanced energy output that can support both immediate energy needs and long-term growth. Their output is more than sufficient to support the energy demands of advanced technologies, from artificial intelligence to large-scale space exploration. This makes them versatile options for different stages of civilization development. In contrast, the lower luminosity of red dwarfs means that a Dyson Sphere would need to be closer to the star, which could make the structure more susceptible to gravitational interactions with the star. However, this proximity also allows for more direct energy capture, potentially increasing the efficiency of the Dyson Sphere. G-type stars provide a good compromise between longevity and energy output, offering enough energy to sustain a growing civilization without the extreme lifespan of red dwarfs. This makes them ideal for civilizations that are expanding rapidly and need a robust energy source to support their growth. The balance they offer is unmatched by other star types. Finally, the choice between a G-type star and a red dwarf ultimately depends on the long-term goals of the Dyson Sphere project. G-type stars are better suited for civilizations seeking immediate and significant energy returns, while red dwarfs are ideal for those prioritizing longevity and stability over eons. Each star type offers distinct advantages that can be leveraged based on the specific needs of the civilization. The distance of the chosen star from Earth is a crucial factor in the feasibility of a Dyson Sphere project. Closer stars offer the advantage of reduced travel time for materials and construction, making them more practical targets. However, proximity also brings challenges, such as increased gravitational effects on Earth and potential risks to our planet's stability. Choosing a star that is too far from Earth introduces significant logistical challenges. The time required to transport materials, personnel, and energy over vast distances could make the project exponentially more complex and costly. Additionally, long-distance communication delays would hinder real-time coordination and management of the construction process. A closer star allows for more direct and timely energy transmission back to Earth, reducing the energy losses that occur over long distances. This proximity also simplifies the infrastructure needed for energy distribution, as less energy is lost in transit, and fewer relay stations are required to maintain the energy flow. However, the gravitational pull of a nearby Dyson sphere could potentially influence Earth's orbit and rotational dynamics. This interaction must be carefully calculated to avoid unintended consequences, such as changes in climate or tidal patterns. The closer the Dyson sphere, the greater the need for precise orbital adjustments and monitoring. A nearby star also poses the risk of increased visibility and potential threats from other civilizations. A Dyson sphere close to Earth could attract attention, leading to possible conflicts or unwanted scrutiny. Balancing proximity with security considerations is essential for ensuring the project remains viable and safe. On the other hand, selecting a distant star could provide greater security and reduce the likelihood of interference from Earth-based or extraterrestrial actors. A more remote location offers the advantage of privacy, allowing the Dyson sphere to operate without drawing undue attention. However, this distance also complicates oversight and maintenance. The energy cost of transporting materials to a distant star would be significantly higher, requiring advanced propulsion technologies and long-term planning. The longer travel times would demand more robust and reliable spacecraft, capable of withstanding extended journeys through space. These challenges increase the overall complexity and duration of the project. A distant Dyson sphere would also face challenges in energy transmission back to Earth. The greater the distance, the more energy is lost during transmission, reducing the efficiency and overall benefit of the Dyson sphere. Advanced transmission methods, such as laser or microwave beams, would be necessary to mitigate these losses. Additionally, the further the star, the more difficult it becomes to provide real-time support and maintenance. Delays in communication and response times could hinder the ability to address issues as they arise, potentially leading to extended downtime or even catastrophic failures. This distance necessitates highly autonomous systems capable of self-repair and adaptation. The choice of distance also impacts the time it would take to complete the Dyson sphere. A closer star allows for faster deployment and construction, enabling quicker energy returns and benefits. Conversely, a distant star could delay the project's completion by decades or even centuries, depending on the technological capabilities at the time. There's also the question of resource availability along the route to the chosen star. A star closer to Earth may be more accessible to asteroid belts or other resource-rich regions that could supply the necessary materials for construction. A distant star, however, might lack nearby resources, requiring more complex supply chains or in-situ resource utilization. Proximity to Earth might also make it easier to monitor and study the effects of the Dyson sphere on the star and surrounding space. This data could be invaluable for future projects, allowing for adjustments and improvements. A distant star would make such monitoring more challenging, limiting our ability to learn from the project. Choosing a closer star could also facilitate collaboration with other Earth-based entities or international coalitions, sharing resources, knowledge, and expertise. This proximity fosters cooperation, reducing the burden on any single entity. However, it also increases the risk of geopolitical tensions if not managed carefully. Ultimately, the ideal distance from Earth for a Dyson sphere balances logistical feasibility, security, energy efficiency, and potential risks. Each factor must be weighed carefully to determine the most suitable location. The decision will shape the project's success and its impact on Earth for generations to come. The longevity of the star is a critical factor in the viability of a Dyson Sphere project. A star with a long, stable life ensures that the energy harvested can sustain civilizations for eons, making the investment worthwhile. Choosing a star with an extended lifespan reduces the need for frequent relocation or rebuilding efforts. Red dwarf stars are often favored for their extraordinary longevity, burning fuel slowly over trillions of years. This slow burn offers a consistent energy source that far exceeds the lifespan of more massive stars. The longevity of red dwarfs makes them ideal for Dyson spheres intended to last through the distant future. In contrast, larger stars, like blue giants, have much shorter lifespans, often just a few million years. While these stars provide immense energy in the short term, their rapid evolution and eventual death pose significant risks. A Dyson sphere around such a star might only be a temporary solution, requiring eventual dismantling or relocation. G-type stars, such as our Sun, offer a middle ground with lifespans in the billions of years. They provide a stable energy source over a significant period, making them suitable for long-term Dyson sphere projects. However, even these stars will eventually evolve into red giants, requiring adaptations or a shift in strategy. The star's evolutionary path must be carefully considered to ensure the Dyson sphere remains viable. As stars age, they undergo changes that can alter their energy output, size, and stability. Understanding these changes is essential for designing a structure that can adapt to or withstand the star's natural progression. Building a Dyson sphere around a star with an unpredictable lifespan could lead to premature failure. Stars that are prone to sudden changes in behavior, such as flare stars or variable stars, introduce risks that could compromise the structure's integrity. Longevity and predictability go hand in hand in ensuring the success of the project. The energy output of the star over its lifetime is another crucial consideration. A star that maintains a consistent energy output over billions of years provides a reliable source of power. In contrast, stars that experience significant fluctuations in energy output may require more complex energy management systems. Stars in the later stages of their life cycle often exhibit increased instability, which can be detrimental to a Dyson sphere. As a star approaches the end of its life, it may expand, contract, or even explode as a supernova. These events would render any Dyson sphere ineffective and potentially destroy the entire structure. Selecting a star with a long and stable lifespan minimizes the risk of such catastrophic events. It allows for the continuous operation of the Dyson sphere, maximizing the return on investment and ensuring a steady supply of energy. Longevity is key to the sustainability of the project over time. The choice of a star with a long lifespan also reduces the need for future interventions. With a stable star, the Dyson sphere can be designed with fewer contingencies for unexpected stellar behavior. This simplicity in design can lead to reduced costs and fewer technological challenges. Stars with longer lifespans also provide more opportunities for scientific research and observation. A Dyson sphere around such a star can serve as a platform for studying the star's life cycle in great detail, offering insights that could inform future projects or other areas of astrophysics. In planning for the long-term operation of a Dyson sphere, it's important to consider the star's endgame. Even stars with long lifespans will eventually exhaust their fuel. Preparing for this eventuality, whether through the design of the Dyson sphere or plans for its eventual dismantling, is crucial for the sustainability of the project. The potential for extending the usefulness of the Dyson sphere even after the star's death should also be considered. Some proposals suggest using the remaining stellar remnants, such as white dwarfs, as energy sources, though the energy available would be significantly less. Such considerations ensure the Dyson sphere remains beneficial even as the star ages. Finally, the longevity of the star impacts the legacy of the Dyson sphere project. A star that lasts for billions or trillions of years ensures that the structure will continue to serve future generations, becoming a long-term monument to the achievements of the civilization that built it. This enduring impact underscores the importance of choosing the right star for such an ambitious endeavor. Star instability presents significant risks to the success of a Dyson Sphere project. Unpredictable changes in the star's behavior can jeopardize the structure's integrity and compromise its ability to collect and transmit energy. Understanding these risks is crucial for developing strategies to mitigate them. One major risk is the occurrence of solar flares, which are sudden eruptions of energy from the star's surface. These flares can release intense bursts of radiation that could damage or disrupt the Dyson Sphere's components. Without proper shielding or adaptive systems, solar flares could lead to catastrophic failures. Another concern is the potential for the star to undergo a sudden change in its energy output. Stars that are nearing the end of their life cycle, or those with inherent instabilities, can experience fluctuations in brightness and energy production. These fluctuations can result in uneven energy collection and distribution, complicating the management of the Dyson Sphere. Stars that rotate rapidly or have irregular magnetic fields are also prone to instability. The interaction between the star's magnetic field and the Dyson Sphere can create electromagnetic disturbances that interfere with the structure's systems. These disturbances might affect energy transmission or cause malfunctions in the sphere's infrastructure. Stars with variable luminosity pose additional challenges. As the star brightens and dims, the amount of energy available to the Dyson Sphere can change dramatically. This variability can strain the energy storage and transmission systems, requiring sophisticated technology to adapt to these shifts in real time. Instabilities within the star can also lead to mass ejections, where the star expels large amounts of plasma and radiation into space. These events can be highly destructive, potentially damaging or destroying sections of the Dyson Sphere. Designing the structure to withstand such forces is essential for its long-term survival. In some cases, stars may experience more extreme forms of instability, such as transitioning into a red giant phase. During this phase, the star expands significantly, which could engulf parts of the Dyson Sphere or force a complete redesign. These changes are difficult to predict and pose serious risks to the project's longevity. The potential for a star to go supernova is the most catastrophic risk of all. A supernova would obliterate the Dyson Sphere and any surrounding structures, rendering the project futile. While supernovas are typically associated with more massive stars, understanding the life cycle of the chosen star is crucial to avoid this devastating outcome. Even less dramatic forms of instability, such as pulsations in the star's core, can have far-reaching effects. These pulsations can alter the star's shape and energy output, creating additional stresses on the Dyson Sphere. Managing these stresses requires precise engineering and continuous monitoring. Stars that are part of a binary or multiple star system introduce another layer of complexity. The gravitational interactions between the stars can lead to unpredictable changes in their orbits and energy output. These dynamics increase the difficulty of maintaining a stable Dyson Sphere and raise the risk of sudden destabilization. A star's chemical composition can also contribute to its instability. Stars with high concentrations of certain elements may be more prone to nuclear reactions that lead to sudden changes in energy production. Understanding the star's internal chemistry is key to assessing the potential for instability and planning accordingly. Stars with high rates of stellar wind can erode the materials of the Dyson Sphere over time. This constant bombardment of particles and radiation can weaken the structure and reduce its lifespan. Protective measures such as advanced shielding or self-repairing materials are necessary to counteract these effects. The presence of star spots, which are cooler regions on the star's surface, can also indicate underlying instability. These spots can affect the star's overall luminosity and create uneven energy distribution across the Dyson Sphere. Monitoring star spots and adjusting the sphere's operations in response can help mitigate these risks. While some instability can be anticipated and managed, the unpredictable nature of stars means that there is always a degree of uncertainty. Advanced modeling and simulations can help predict potential issues, but real-time adaptation and resilience are critical for coping with unexpected changes. Finally, the inherent risks of star instability highlight the importance of choosing the right star for the Dyson Sphere. A thorough understanding of the star's characteristics and potential for instability is essential to minimize risks and ensure the long-term success of the project. Planning for these challenges from the outset is crucial for building a Dyson Sphere that can withstand the test of time. Choosing the ideal materials for a Dyson Sphere is one of the most critical decisions in its design. These materials must withstand the extreme conditions near a star while being lightweight enough for construction in space. Strength, durability, and efficiency are key factors in material selection. Carbon nanotubes are often considered due to their extraordinary tensile strength and low weight. These materials can provide the structural integrity needed to hold the Dyson Sphere together, while minimizing the amount of material required. Their strength-to-weight ratio is unmatched, making them a top candidate for large-scale space structures. Graphene, another advanced material, offers exceptional electrical conductivity and strength. Its ability to conduct heat and electricity efficiently makes it an excellent choice for energy transmission within the Dyson Sphere. Graphene's flexibility also allows it to be used in various structural components and energy collection systems. Silicon-based materials are ideal for photovoltaic panels that would cover the Dyson Sphere. Silicon is already widely used in solar panels on Earth due to its effectiveness in converting sunlight into electricity. Advanced silicon composites could further enhance energy capture efficiency, making it a vital material for the sphere. For shielding against radiation, materials like boron nitride nanotubes are considered. These materials can protect the structure from the intense radiation emitted by the star, ensuring the longevity of the Dyson Sphere's components. Effective shielding is essential to prevent damage and maintain the sphere's functionality. Aluminum alloys are another potential material, valued for their lightweight and corrosion-resistant properties. These alloys could be used in the construction of the sphere's framework, providing a strong yet flexible skeleton for the structure. Their resistance to space weathering makes them durable for long-term use. The Dyson Sphere's reflective surfaces could be coated with materials like silver or aluminum to enhance their ability to redirect and concentrate sunlight. These reflective materials would maximize energy collection by ensuring that as much of the star's energy as possible is captured and utilized. For structural elements that require high thermal resistance, materials like tungsten might be used. Tungsten's high melting point makes it ideal for components that will be exposed to the star's intense heat. Its durability at high temperatures ensures the structural integrity of the Dyson Sphere in the most extreme conditions. To manage the thermal expansion of the Dyson Sphere, materials with low thermal expansion coefficients, such as INVAR, might be incorporated. These materials prevent the structure from warping or breaking as temperatures fluctuate, maintaining the Dyson Sphere's stability over time. The use of metamaterials, which have properties not found in naturally occurring substances, could offer unique advantages. These materials can be engineered to exhibit specific behaviors, such as bending light or sound in unconventional ways. Metamaterials might be used in advanced energy collection or transmission systems within the Dyson Sphere. For the construction process itself, materials that are easily fabricated in space, such as lunar or asteroid regolith, could be utilized. These materials are abundant and can be processed into usable forms with minimal energy, reducing the need for transporting materials from Earth. In-situ resource utilization is crucial for minimizing costs. Nanomaterials might also play a role in self-repairing systems within the Dyson Sphere. These materials could detect and repair damage at the molecular level, ensuring that the structure remains operational without constant human intervention. This self-sustaining capability is vital for the long-term viability of the project. Ceramics with high thermal and mechanical strength could be used for insulating parts of the Dyson Sphere. These ceramics can withstand the star's intense heat, while protecting other components from thermal stress. Their stability under extreme conditions makes them a valuable addition to the material mix. Advanced polymers could serve in flexible components that need to move or adjust, such as solar sails or antennae. These materials offer durability and resilience while being lightweight and adaptable. Polymers designed for space applications ensure that moving parts function smoothly in the harsh environment of space. Finally, the combination of these materials must be carefully balanced to create a Dyson Sphere that is both functional and sustainable. Each material brings specific strengths to the table, and their integration must be optimized to handle the unique challenges of constructing and maintaining a megastructure in space. This careful selection and combination of materials are key to turning the Dyson Sphere from a theoretical concept into a reality. Mining resources in space is a critical component of constructing a Dyson Sphere. The sheer volume of materials required makes it impractical to transport everything from Earth. Instead, we must look to the vast resources available within our solar system and beyond. Asteroids are among the most promising sources of raw materials. These space rocks contain valuable metals like iron, nickel, and cobalt, which are essential for building the structural framework of the Dyson Sphere. Mining asteroids offers a way to access these materials without the constraints of Earth's gravity. The Moon is another potential resource hub. Its surface is rich in silicon, aluminum, and other elements that could be used in construction. The reduced gravity on the Moon also makes it easier to launch mined materials into space, making it a strategic location for mining operations. Mining on Mars presents another opportunity, especially for water and minerals that can be used in life support systems and manufacturing processes. The Red Planet's resources could support both the construction of the Dyson Sphere and the establishment of permanent bases in space. To extract these resources, we'll need advanced robotic mining technologies. These machines must be capable of operating in harsh environments with minimal human intervention. Autonomous systems will be key to efficiently mining and processing materials in the vacuum of space. Space mining also requires refining materials on site. Transporting raw ore back to Earth or other locations is inefficient, so processing must occur where the materials are found. This involves developing mobile refineries that can convert ore into usable metals and other products directly in space. The use of solar energy to power these mining operations is crucial. The abundance of sunlight in space provides a reliable and continuous energy source for mining and processing activities. Solar-powered mining equipment reduces the need for fuel and other Earth-sourced energy supplies. Transporting mined materials from asteroids or moons to the construction site of the Dyson Sphere is another challenge. Spacecraft equipped with efficient propulsion systems, such as ion thrusters, will be necessary to move large quantities of material across vast distances. Mining operations must also account for the environmental impact. While space is vast, the extraction of resources from celestial bodies could have unforeseen consequences. Sustainable mining practices will be essential to avoid depleting these resources or causing instability in the bodies being mined. The legal and ethical implications of space mining are also significant. International agreements will be needed to regulate who can mine which resources and how those resources are used. Establishing clear guidelines will help prevent conflicts and ensure that space mining benefits all of humanity. Developing infrastructure to support space mining is another hurdle. This includes building space stations, refueling depots, and communication networks that enable mining operations to function smoothly. This infrastructure is the backbone of any successful space mining enterprise. Long-term storage of mined materials in space requires special considerations. Materials must be protected from cosmic radiation, temperature extremes, and micrometeoroid impacts. Designing secure storage solutions is vital to preserving resources until they are needed for construction. Recycling in space will also play a crucial role. Mining operations will inevitably produce waste materials, but many of these can be repurposed. Developing efficient recycling systems ensures that nothing goes to waste, further reducing the need to extract new resources. The scale of space mining operations needed for a Dyson Sphere is unprecedented. Coordinating multiple mining sites across the solar system will require advanced logistical planning and real-time communication. This coordination ensures that all necessary materials are available when and where they're needed. In the end, space mining is about more than just resource extraction. It's about laying the groundwork for humanity's future in space. By developing the technology and infrastructure to mine and use space resources, we take the first steps toward becoming a true interstellar civilization. These efforts are essential for the success of the Dyson Sphere and beyond. Nanotechnology plays a pivotal role in the construction of a Dyson Sphere, offering solutions that traditional engineering cannot. By manipulating materials at the atomic level, nanotechnology enables the creation of ultra-strong and lightweight structures that are essential for a project of this scale. These nanomaterials can be designed to exhibit properties that surpass those of conventional materials. One of the key applications of nanotechnology in a Dyson Sphere is in the development of carbon nanotubes. These nanotubes are incredibly strong and flexible, making them ideal for use in the structural framework of the Dyson Sphere. Their ability to conduct electricity and heat efficiently also enhances the overall functionality of the structure. Advanced alloys, enhanced with nanoparticles, offer significant advantages over traditional metals. By incorporating nanomaterials into these alloys, we can achieve greater strength, durability, and resistance to extreme temperatures. These properties are crucial for components that will be exposed to the intense heat and radiation near a star. The use of nanotechnology also extends to the energy collection systems within the Dyson Sphere. Nanostructured materials can be used to create more efficient photovoltaic cells, increasing the amount of energy captured from the star. These cells can be engineered to capture a broader spectrum of light, maximizing the energy harvested. Nanotechnology enables the creation of self-healing materials, which are particularly valuable for maintaining the Dyson Sphere over long periods. These materials can repair themselves at the molecular level, addressing wear and tear without the need for human intervention. This self-repair capability ensures the longevity and reliability of the structure. Advanced alloys developed through nanotechnology can also be designed to resist corrosion and degradation in the harsh environment of space. These materials maintain their integrity over time, reducing the need for frequent replacements or repairs. The result is a more sustainable and durable Dyson Sphere. The lightweight nature of nanomaterials allows for the construction of larger, more complex structures without the associated weight penalties. This is particularly important for a Dyson Sphere, where reducing mass is critical to maintaining stability and reducing the energy required for construction and maintenance. Nanotechnology can also enhance the thermal management systems within the Dyson Sphere. Nanomaterials with high thermal conductivity can be used to dissipate heat more effectively, preventing overheating of critical components. This ensures that the Dyson Sphere operates efficiently even under the intense heat of a star. Incorporating nanotechnology into the manufacturing process allows for the precise assembly of components at the molecular level. This precision reduces the margin for error and increases the overall quality of the construction. It also enables the creation of complex designs that would be impossible with traditional manufacturing techniques. The development of advanced alloys using nanotechnology can lead to materials that are both stronger and lighter than anything currently available. These materials can be tailored to meet the specific demands of the Dyson Sphere, providing the necessary strength while minimizing weight. This customization is essential for optimizing the structure's performance. Nanotechnology also offers solutions for energy storage within the Dyson Sphere. Nanomaterials can be used to create high-capacity batteries or supercapacitors that store large amounts of energy in a compact form. This energy storage capability is crucial for balancing energy supply and demand within the structure. The flexibility of nanomaterials allows for the design of adaptive systems that can respond to changes in the environment. These systems can adjust their properties in real time to optimize performance, whether it's adjusting the angle of solar panels or reinforcing structural elements during periods of increased stress. Nanotechnology can also improve the efficiency of resource utilization during the construction of the Dyson Sphere. By using nanomaterials, less raw material is needed to achieve the same or greater structural strength. This efficiency reduces the overall resource demand, making the project more sustainable. The potential of nanotechnology and advanced alloys in the construction of a Dyson Sphere cannot be overstated. These innovations not only make the project feasible, but also open the door to new possibilities in space exploration and megastructure design. By leveraging these cutting-edge technologies, we can build a Dyson Sphere that is both resilient and efficient. Ultimately, nanotechnology and advanced alloys represent the future of construction in space. Their unique properties allow for the creation of structures that are not only stronger and lighter, but also more adaptable and sustainable. These materials are the foundation upon which the Dyson Sphere will be built, enabling us to harness the power of a star and propel humanity into a new era of technological achievement. Transporting materials from various points in space to the Dyson Sphere construction site presents one of the most significant logistical challenges. The vast distances involved require efficient propulsion systems capable of moving large quantities of material with minimal energy expenditure. Advanced propulsion technologies, such as ion thrusters or solar sails, offer promising solutions for these long-haul missions. One key strategy for reducing transportation costs is to utilize resources that are already in space, minimizing the need to lift materials out of Earth's gravity well. By mining asteroids, moons, and other celestial bodies, we can gather the necessary materials closer to the construction site. This approach not only conserves energy, but also speeds up the overall construction timeline. Once materials are transported to the assembly site, the challenge shifts to the precise assembly of the Dyson Sphere's components. Given the scale and complexity of the structure, automated robotic systems will likely be employed to handle much of the construction. These robots must be capable of performing tasks with a high degree of precision, ensuring that each component fits perfectly into place. Autonomous construction systems will need to work seamlessly in the vacuum of space, where traditional methods like welding and bolting might not be practical. Techniques such as cold welding, where metals bond without the need for heat, could be crucial in assembling the Dyson Sphere's framework. This method reduces the need for additional energy sources, making it more efficient in space. Another critical aspect of assembly is the coordination of multiple construction teams and systems across vast distances. This coordination requires advanced communication networks, capable of transmitting data with minimal delay. Real-time adjustments and monitoring are essential to ensure that the assembly process proceeds smoothly and efficiently. Transporting large structural elements poses additional challenges. These components must be designed for easy deployment and assembly in space, often requiring modular designs that can be connected and expanded as needed. This modular approach allows for greater flexibility in construction and helps mitigate risks associated with transporting massive structures. The sheer scale of the Dyson Sphere means that construction will likely occur simultaneously in multiple locations. This distributed approach necessitates a high level of coordination and synchronization to ensure that all parts of the structure are assembled correctly and on schedule. Any misalignment or delay could have significant consequences for the project. To manage the assembly process, advanced AI systems could oversee and optimize the placement of materials and components. These AI systems would be responsible for making real-time decisions about where to deploy resources, how to position components, and how to address any issues that arise during construction. Their ability to process vast amounts of data quickly will be crucial for maintaining efficiency. In addition to AI, human oversight will remain a vital part of the construction process. Engineers and technicians will likely monitor the assembly remotely, making critical adjustments and providing expertise that cannot yet be fully replicated by machines. This human-machine collaboration is essential for the success of such a complex project. Transporting energy to power the construction process is another challenge. Solar power stations could be set up in space to provide a continuous energy supply to the construction robots and systems. These stations would harness the star's energy directly, reducing the need to transport fuel from Earth and ensuring a steady power supply throughout the construction. The construction process must also account for the movement and positioning of materials in a zero-gravity environment. This requires specialized equipment designed to stabilize and position components accurately in space. Tools like magnetic clamps or tractor beams might be used to hold materials in place during assembly, ensuring precision and stability. To protect materials during transport, advanced shielding techniques will be necessary to prevent damage from cosmic radiation, micrometeoroids, and other space hazards. Ensuring that materials arrive intact is crucial for maintaining the integrity of the Dyson Sphere as it is assembled. These protective measures must be lightweight and effective, balancing durability with ease of transport. Assembling the Dyson Sphere will also involve careful planning to avoid collisions with existing satellites, space debris, or other objects in orbit. Detailed mapping and tracking of all nearby objects will be essential to ensure a safe construction environment. This proactive approach helps prevent accidents that could delay or jeopardize the entire project. Finally, the scalability of the Dyson Sphere's design allows for incremental assembly. The structure can be built in stages, with each completed section contributing to the overall energy collection. This phased approach allows for testing and refinement during construction, ensuring that each part of the Dyson Sphere functions as intended before moving on to the next stage. In the end, the transportation and assembly of materials for a Dyson Sphere require a combination of innovative technologies, precise coordination, and careful planning. Overcoming these challenges is essential to realizing the vision of harnessing the power of a star, and it represents one of the greatest engineering feats humanity has ever undertaken. Micrometeoroid impacts are a constant threat to any structure in space, including a Dyson Sphere. These tiny particles travel at incredibly high speeds, and even a small impact can cause significant damage. To ensure the Dyson Sphere's long-term integrity, it must be equipped to withstand these impacts. One of the most effective strategies for dealing with micrometeoroids is to use advanced shielding materials. These materials can absorb and dissipate the energy of an impact, preventing it from penetrating the structure. Layered shielding, where multiple layers of different materials are used, can provide enhanced protection by spreading out the force of an impact. Self-repairing materials offer another line of defense. These materials can automatically heal small cracks or holes caused by micrometeoroid impacts. By incorporating self-repairing properties into the Dyson Sphere's structure, the overall durability of the sphere is significantly increased, reducing the need for frequent repairs. The use of redundant systems is also crucial. If one part of the Dyson Sphere is damaged by a micrometeoroid, other systems should be able to take over its functions temporarily. This redundancy ensures that the Dyson Sphere continues to operate effectively, even if part of the structure is compromised. Monitoring systems can detect micrometeoroid impacts in real time. These systems use sensors to track the location and severity of impacts, allowing for immediate response and repair. By quickly identifying and addressing damage, the Dyson Sphere can maintain its functionality and prevent minor issues from escalating. To further protect the Dyson Sphere, debris clearing systems might be employed. These systems could use lasers, magnetic fields, or other technologies to divert or destroy micrometeoroids before they reach the structure. Proactively managing the environment around the Dyson Sphere helps minimize the risk of impact. The positioning of the Dyson Sphere components can also influence their vulnerability to micrometeoroid impacts. By placing the most critical and sensitive parts of the structure in areas with lower impact risk, the overall resilience of the Dyson Sphere can be improved. Strategic positioning is an essential part of the design process. Building the Dyson Sphere with modularity in mind allows for easy replacement of damaged sections. If a segment is severely impacted, it can be swapped out with minimal disruption to the overall structure. This modular approach ensures that the Dyson Sphere remains operational even after significant damage. Micrometeoroid impacts can also affect the energy collection systems of the Dyson Sphere. Protecting photovoltaic panels and other energy harvesting components from these impacts is crucial for maintaining the energy output of the structure. Shielding these systems without reducing their efficiency is a key challenge. The velocity and trajectory of micrometeoroids must be carefully studied to develop effective countermeasures. Understanding the patterns and behaviors of these particles allows for more precise design and placement of shielding and monitoring systems. This data-driven approach enhances the Dyson Sphere's defenses. Incorporating flexible materials in some parts of the Dyson Sphere can help absorb the impact energy. Flexible components can bend or deform slightly upon impact, reducing the risk of fracture or significant damage. This flexibility is particularly useful in areas where rigidity could lead to structural failure. Nanotechnology offers innovative solutions for dealing with micrometeoroid impacts. Nanocoatings can be applied to the surface of the Dyson Sphere to provide additional protection against impacts. These coatings can be designed to self-repair or harden upon contact, adding an extra layer of resilience. The constant threat of micrometeoroids requires continuous maintenance and upgrades to the Dyson Sphere. Regular inspections and the ability to quickly replace or repair damaged sections are essential for ensuring the structure's longevity. A proactive maintenance strategy is vital for dealing with the wear and tear caused by these impacts. In the long run, developing new materials and technologies specifically designed to counter micrometeoroid impacts will be crucial. Research and innovation in this area will lead to better protection and longer-lasting structures in space. The ongoing advancement of space technology will play a key role in safeguarding the Dyson Sphere. Ultimately, dealing with micrometeoroid impacts is about creating a resilient and adaptable Dyson Sphere. By combining advanced materials, proactive defense systems, and strategic design, we can ensure that the Dyson Sphere remains functional and efficient, even in the face of these constant space hazards. Photovoltaic panels are one of the most straightforward and widely used methods for converting sunlight into electricity. They harness the energy of photons to generate power, making them an obvious choice for a Dyson Sphere. Their efficiency and maturity as a technology make them a reliable option for large-scale energy collection. However, photovoltaic panels have limitations, particularly when it comes to efficiency and the spectrum of light they can capture. Most panels are optimized for visible light, meaning they miss out on a significant portion of the star's total energy output. This limitation prompts the exploration of other methods that can capture a broader range of the electromagnetic spectrum. One alternative to traditional photovoltaic panels is the use of multi-junction solar cells. These cells are designed to capture different wavelengths of light by stacking multiple layers, each tuned to a specific part of the spectrum. This approach increases the overall efficiency of energy conversion, making it more suitable for the vast energy needs of a Dyson Sphere. Another method involves thermophotovoltaic systems, which convert heat into electricity. By capturing the infrared radiation emitted by the star, these systems can generate power even from the star's thermal energy. This technology complements photovoltaic panels by utilizing parts of the spectrum that conventional panels cannot access. Solar thermal power, which uses mirrors or lenses to concentrate sunlight onto a small area to generate heat, is another viable option. The heat produced can drive turbines or engines to generate electricity, providing a different approach to harnessing solar energy. This method is particularly useful in scenarios where direct electricity generation from light is less efficient. Laser-based energy transmission is another advanced method being considered. In this approach, energy collected by the Dyson Sphere could be converted into high-powered laser beams and transmitted to distant locations. This method allows for efficient long-distance energy transfer, bypassing some of the limitations of traditional electricity grids. Microwave transmission is similar to laser-based methods, but uses microwave frequencies to transmit energy. This technique is particularly effective over long distances, and can be used to send power from the Dyson Sphere to planets or space stations without significant loss. Microwaves can penetrate dust and other obstacles that might block other forms of energy transmission. Each of these methods offers unique advantages and challenges, depending on the specific design and goals of the Dyson Sphere. Photovoltaic panels are simpler and more established, but alternative methods could significantly boost the overall energy capture and efficiency. Combining these technologies could create a more versatile and resilient energy collection system. The choice between photovoltaic panels and other methods also depends on the availability of materials and the environmental conditions around the star. Some technologies might perform better in different parts of the Dyson Sphere, allowing for a hybrid approach that maximizes energy capture across the entire structure. Maintenance and longevity are also critical factors. Photovoltaic panels are relatively easy to maintain, but some of the more advanced systems, like thermophotovoltaics or laser-based methods, might require more complex upkeep. The long-term operation of the Dyson Sphere depends on selecting technologies that can endure the harsh conditions of space. The scalability of each method is another consideration. Photovoltaic panels are modular and can be deployed incrementally, allowing the Dyson Sphere to gradually expand its energy collection capabilities. More advanced methods may require a more integrated approach, potentially limiting their flexibility during the construction phase. The energy conversion efficiency of each method must be weighed against its cost and complexity. While some advanced technologies offer higher efficiency, they might also come with greater technical challenges and higher costs. Balancing these factors is crucial to ensuring that the Dyson Sphere remains economically viable. The integration of multiple energy collection methods can also provide redundancy, ensuring that the Dyson Sphere continues to operate even if one system fails. This redundancy is key to the reliability of the structure, preventing total energy loss in the event of damage or malfunction. Ultimately, the decision between photovoltaic panels and other methods will be driven by the specific energy demands of the Dyson Sphere and the technologies available at the time of construction. The ideal solution may involve a combination of these approaches, tailored to the unique challenges and opportunities presented by the chosen star and its environment. Wireless energy transmission is a critical component of the Dyson Sphere's functionality, enabling the transfer of vast amounts of energy over long distances. Two of the most promising methods for this are microwave transmission and laser-based transmission, each with its own set of advantages and challenges. Microwave transmission works by converting the energy collected by the Dyson Sphere into microwaves, which are then beamed to a receiving station, such as a planet or space station. Microwaves are particularly effective because they can travel long distances without significant loss of energy, making them ideal for space applications. One of the main benefits of microwave transmission is its ability to penetrate through obstacles like dust and clouds, which can block other forms of electromagnetic radiation. This makes it a reliable method for consistent energy delivery, even in less than ideal conditions. However, precise targeting is essential to avoid energy loss and ensure the microwaves reach their intended destination. Laser-based energy transmission, on the other hand, uses focused beams of light to transmit energy. Lasers can be extremely efficient over vast distances, especially in the vacuum of space where there is no atmospheric interference. The high precision of laser beams allows for targeted energy delivery, which is crucial for minimizing losses. Lasers offer the advantage of being able to concentrate energy into a very small area, making them ideal for powering specific devices or stations that require high energy density. However, this precision also requires highly accurate targeting systems to ensure the beam remains focused on its target, especially over astronomical distances. Both methods require advanced technology to convert the collected solar energy into microwaves or laser light, and then back into usable electrical energy at the receiving end. The efficiency of these conversion processes directly impacts the overall effectiveness of the energy transmission system, making it a key area of development. Safety is a significant concern with both microwaves and lasers, as misdirected beams could cause damage to equipment or even pose risks to life. Protective measures and fail-safes must be integrated into the system to prevent accidental exposure to these powerful energy beams, ensuring the safe operation of the Dyson Sphere. The infrastructure required for microwave or laser transmission includes not just the transmission devices on the Dyson Sphere, but also large receiving arrays on the target planets or space stations. These receiving stations must be capable of capturing and converting the transmitted energy with high efficiency to maximize the benefits of the Dyson Sphere. The alignment between the Dyson Sphere and the receiving stations must be maintained with great precision. Any misalignment could result in significant energy loss or even complete transmission failure. Continuous monitoring and adjustment are necessary to keep the energy beams on target as both the Dyson Sphere and the receiving stations move through space. Laser-based transmission can also be used for communication purposes, providing a dual function for the infrastructure. This versatility makes lasers an attractive option, particularly for missions that require both power transmission and high-speed data links. Integrating these functions could streamline the design of the Dyson Sphere's transmission systems. Microwave transmission, while generally more robust, might face challenges from interference with other communication systems. Ensuring that the transmission frequencies used for energy transfer do not overlap with those used for communication or other technologies is essential to avoid conflicts and maintain efficient operation. The choice between microwaves and lasers may also be influenced by the distance over which energy needs to be transmitted. Lasers, with their focused beams, are better suited for longer distances, while microwaves may be more effective for relatively shorter transmissions within a star system. This distinction will shape the design of the transmission infrastructure. Energy losses during transmission are inevitable, but minimizing these losses is critical to the Dyson Sphere's overall efficiency. Both microwave and laser systems must be optimized to reduce energy dissipation and ensure that the maximum possible amount of energy reaches the receiving stations. The development of these wireless transmission systems will require significant advancements in materials, science, optics, and electronics. Innovations in these areas will enable the Dyson Sphere to transmit energy more effectively, making the project not only feasible, but also sustainable over the long term. Ultimately, the choice between microwave and laser transmission, or a combination of both, will depend on the specific needs of the Dyson Sphere and its intended energy recipients. Each method offers unique benefits that can be leveraged to create a robust and efficient energy transmission system, ensuring that the power harnessed from the star can be effectively used wherever it is needed. The efficiency of energy collection is a critical factor in the overall success of a Dyson Sphere. Maximizing the amount of energy captured from the star determines how effectively the structure can power civilizations and support advanced technologies. Every aspect of the Dyson Sphere's design is influenced by the need to optimize this efficiency. Photovoltaic panels, one of the primary methods for collecting energy, have varying degrees of efficiency depending on their material and construction. Traditional silicon-based panels typically convert about 20% of the sunlight they receive into electricity. However, advancements in multi-junction cells and nanomaterials are pushing these limits, allowing for higher conversion rates. Positioning of the panels plays a crucial role in maximizing energy capture. Panels must be angled and distributed in a way that ensures they receive continuous sunlight, minimizing any shadowing effects from other parts of the structure. This careful alignment is essential to avoid energy losses due to suboptimal exposure. Another factor influencing efficiency is the quality of the materials used. High-quality, low-defect materials lead to better performance in energy collection. Materials that degrade slowly over time also maintain their efficiency longer, reducing the need for frequent replacements and ensuring consistent energy output. The wavelength of light captured also impacts efficiency. Most photovoltaic systems are designed to capture visible light, but a significant portion of a star's energy output is in the infrared and ultraviolet spectra. Multi-junction cells that can harness a broader range of wavelengths offer a way to increase overall efficiency by tapping into these additional energy sources. Thermal management is another key element in maintaining efficiency. Solar panels and other energy collection systems can lose efficiency as they overheat. Incorporating effective cooling mechanisms such as heat sinks or radiative cooling surfaces ensures that these systems operate at their optimal temperature, preserving their ability to generate power. Reflective surfaces can be used to redirect light onto the energy collection areas, concentrating sunlight and boosting the amount of energy captured. This approach is particularly useful in areas where direct sunlight is weaker or more diffuse, allowing for a more uniform and efficient energy collection across the Dyson Sphere. The distribution of energy collected is also crucial for maintaining efficiency. Efficient energy storage and transmission systems must be in place to ensure that the power generated is used effectively without significant losses. Batteries, capacitors, and other storage devices must be optimized for both capacity and discharge rates to match the needs of the structure. Energy conversion systems must also be optimized to reduce losses during the transition from sunlight to electricity. Advanced converters that minimize the energy lost during this process are essential for improving the overall efficiency of the Dyson Sphere. The integration of these systems into the structure needs to be seamless to avoid additional energy losses. The environment in which the Dyson Sphere operates also affects efficiency. Dust, micrometeoroids, and other space debris can accumulate on energy collection surfaces, reducing their effectiveness. Regular maintenance and cleaning systems, potentially involving autonomous drones, are necessary to keep the panels operating at peak efficiency. Energy collection systems must also be resilient to the natural variations in the star's output. Periods of increased solar activity, such as flares or sunspots, can cause fluctuations in energy production. Designing systems that can adapt to these changes without significant efficiency drops is key to maintaining a stable energy supply. Energy conversion technologies are continuously evolving, and integrating the latest advancements into the Dyson Sphere will be essential for maintaining high efficiency over time. As new materials and methods are developed, they can be incorporated into the existing structure, ensuring that the Dyson Sphere remains at the cutting edge of energy collection. The scale of the Dyson Sphere also impacts efficiency. Larger structures can capture more energy, but they also require more resources to build and maintain. Finding the right balance between size and efficiency is crucial for optimizing the overall performance of the Dyson Sphere. Finally, the long-term efficiency of the Dyson Sphere will depend on continuous monitoring and adjustment. Sensors and AI systems will play a vital role in tracking the performance of energy collection systems and making real-time adjustments to optimize efficiency. This dynamic approach ensures that the Dyson Sphere operates at its full potential throughout its lifespan. Managing energy surpluses is a critical aspect of operating a Dyson Sphere. Given the immense power generated, there will be times when the energy produced exceeds immediate needs. Efficiently storing or redirecting this surplus is essential to prevent waste and ensure energy availability during periods of high demand. One of the primary methods for handling excess energy is through large-scale energy storage systems. Advanced batteries, supercapacitors, and other storage technologies can hold surplus energy until it's needed. These systems must be capable of storing vast amounts of energy without significant losses over time. Another approach is to use the surplus energy to produce storable fuels, such as hydrogen through electrolysis. This hydrogen can then be stored and used as a clean energy source when direct solar power is unavailable. Converting surplus energy into chemical form provides a flexible and transportable energy reserve. Surplus energy can also be directed toward non-essential but beneficial activities. For instance, it could power large-scale scientific research, such as particle accelerators or space exploration missions. By channeling excess energy into these projects, the Dyson Sphere can support advancements that would otherwise be impossible. In some cases, the surplus energy might be used to create or expand infrastructure. Building additional energy collection systems, expanding habitats, or constructing new technologies could all be driven by excess power. This proactive use of surplus energy helps ensure that the Dyson Sphere continues to grow and evolve. Thermal energy management is another key consideration. Excess energy, particularly in the form of heat, must be dissipated to prevent overheating. Radiative cooling systems or heat sinks can be employed to manage this thermal surplus, ensuring that the Dyson Sphere maintains optimal operating conditions. Excess energy could also be distributed to other locations, such as nearby planets or space stations. Wireless transmission systems, like those using microwaves or lasers, can beam surplus energy to distant locations, ensuring that no power goes to waste. This redistribution helps balance energy supply across a wider area. Developing smart grid systems within the Dyson Sphere allows for real-time management of energy surpluses. These systems can automatically adjust the distribution and storage of energy based on current demand and future projections. Smart grids ensure that energy is used efficiently, regardless of fluctuations in production. In some scenarios, it might be necessary to temporarily reduce energy collection to prevent overloading storage systems. Adjustable panels or reflectors can be used to limit the amount of sunlight captured, reducing energy generation during periods of low demand. This flexibility helps maintain balance within the Dyson Sphere's energy network. The ability to export energy to other star systems could become a valuable asset. By converting surplus energy into highly focused beams, the Dyson Sphere could supply power to distant civilizations or spacecraft. This interstellar energy trade could open new avenues for cooperation and economic exchange. Surplus energy management also involves long-term planning. Predicting future energy needs and potential technological advancements allows for better allocation of surplus power today. By investing in future-oriented projects, the Dyson Sphere can ensure that its energy production continues to benefit its creators for generations. Surplus energy might also be used for environmental control within the Dyson Sphere. Maintaining artificial climates, generating oxygen, or recycling waste could all be powered by excess energy. These processes are crucial for sustaining life and ensuring the Dyson Sphere's habitability. Developing emergency response systems that can quickly absorb or redirect surplus energy is essential for safety. In the event of unexpected spikes in energy production, these systems can prevent overloads that might damage infrastructure. Quick response capabilities are key to maintaining the Dyson Sphere's integrity. Using surplus energy to power educational and cultural initiatives could help advance knowledge and preserve history. Creating vast digital archives, immersive simulations, or even new forms of art could be driven by the excess power generated. These initiatives enrich the civilization that built the Dyson Sphere, making the most of its energy potential. Ultimately, managing energy surpluses requires a combination of advanced technology, strategic planning, and creative thinking. The ability to harness and direct this surplus effectively will determine how well the Dyson Sphere can sustain its creators and contribute to their ongoing development. The infrastructure for energy distribution within a Dyson Sphere is as critical as the energy collection itself. Efficiently moving energy from the collection points to where it's needed requires a well-designed network of transmission systems. This infrastructure must handle the immense scale of power generated while minimizing losses. Superconducting materials offer a solution for reducing energy loss during transmission. By enabling electricity to flow without resistance, these materials ensure that nearly all the energy collected can be delivered to its destination. Implementing superconductors throughout the Dyson Sphere's grid is key to maximizing efficiency. The layout of transmission lines must be optimized to handle the vast distances within the Dyson Sphere. A hub-and-spoke design, where energy is funneled to central nodes before being distributed, can help manage the complexity. This network must be robust enough to maintain steady power flow, even with variable energy inputs. Wireless energy transmission methods, such as microwaves or lasers, are crucial for moving energy across space within the Dyson Sphere. These systems allow for the transfer of power without the need for physical cables, reducing the potential for maintenance issues and making the distribution network more flexible. Power management systems are essential for balancing supply and demand across the Dyson Sphere. These systems must be capable of adjusting distribution in real time, directing energy where it's needed most. By using advanced algorithms, the Dyson Sphere can maintain a stable energy output, even as conditions change. Energy storage facilities need to be strategically placed throughout the distribution network. These storage sites act as buffers, absorbing excess energy during periods of low demand and releasing it when consumption rises. Their placement is critical for maintaining consistent power availability. The infrastructure must also be designed to handle surges and fluctuations in energy production. This includes installing surge protectors and energy dissipation systems that can absorb excess power without damaging the grid. Ensuring the stability of the transmission network is vital for the Dyson Sphere's long-term operation. Maintaining the infrastructure requires automated systems capable of performing repairs and upgrades. Drones or robotic maintenance units could patrol the network, identifying and fixing issues before they escalate. Automation ensures that the energy distribution system remains operational with minimal human intervention. The integration of communication networks into the energy distribution infrastructure enhances its efficiency. By linking power management systems with real-time data from sensors, the Dyson Sphere can dynamically adjust its energy flow. This connectivity allows for smarter, more responsive energy distribution. The durability of the distribution infrastructure is another key consideration. Materials must be chosen for their ability to withstand the harsh conditions of space, including radiation, extreme temperatures, and micrometeoroid impacts. Ensuring the longevity of the infrastructure is crucial for the Dyson Sphere's success. Energy distribution within the Dyson Sphere also involves managing the directional flow of power. Systems must be in place to prevent feedback loops or energy waste, ensuring that all power is directed toward useful ends. This requires precise control over how energy moves through the network. The scalability of the distribution infrastructure is essential to accommodate future expansions of the Dyson Sphere. As new sections are added, the network must be capable of integrating additional power sources seamlessly. This flexibility allows the Dyson Sphere to grow and evolve over time. Safety measures are a critical component of the infrastructure. Redundant systems, fail-safes, and emergency shut-off mechanisms must be integrated to protect the grid from overloads or failures. Ensuring the safety of the energy distribution system is vital to prevent catastrophic damage. The environmental impact of the energy distribution network must also be considered. Minimizing the heat generated by transmission and reducing the electromagnetic interference are important for maintaining the Dyson Sphere's internal environment. Sustainable design principles help ensure the long-term viability of the infrastructure. Ultimately, the infrastructure for energy distribution within the Dyson Sphere must be a blend of cutting-edge technology, strategic planning, and adaptability. Its success depends on creating a network that is efficient, reliable, and capable of evolving with the needs of the civilization it powers. Autonomous robotic construction is a cornerstone of building a Dyson Sphere. Given the immense scale and complexity of the project, human labor alone is insufficient to complete the task. Robots designed for autonomous operation can work continuously, assembling the structure with precision and efficiency. These robots must be capable of operating in the harsh conditions of space. They need to withstand extreme temperatures, radiation, and micrometeoroid impacts while maintaining their functionality. Durability is key to ensuring that they can perform their tasks without frequent maintenance or replacement. Advanced AI systems will guide the robots, allowing them to make decisions in real time. This includes navigating the construction site, identifying where components need to be placed, and adapting to unexpected challenges. The ability to operate independently is crucial for maintaining progress on such a vast project. Robots will be equipped with a variety of tools and capabilities to handle different aspects of construction. From welding and assembly to material transport and surface finishing, these machines must be versatile. Modular designs allow robots to switch tools or functions as needed, increasing their overall utility. The coordination of thousands or even millions of robots requires a highly organized system. Centralized AI will manage these robots, ensuring they work together seamlessly. This coordination is essential for preventing collisions, optimizing workflows, and maintaining a steady pace of construction. One of the challenges in autonomous construction is ensuring precision. Even minor errors in alignment or assembly could have significant repercussions given the scale of the Dyson Sphere. High-resolution sensors and precise control mechanisms enable robots to place components with exacting accuracy. Energy management is also a consideration for autonomous robots. They need to be powered efficiently, whether through solar energy, stored energy reserves, or wireless energy transmission from the Dyson Sphere itself. Ensuring that robots have a consistent power supply is critical to avoid interruptions in construction. Robots must be capable of self-repair and maintenance to reduce downtime. If a robot encounters a malfunction, it should be able to diagnose the issue and perform repairs autonomously. This self-sufficiency is vital for minimizing delays and keeping the project on track. Autonomous robots will also play a role in transporting materials to the construction site. This includes moving components from storage areas to their designated assembly points. Efficient logistics management by these robots ensures that materials are available exactly when and where they are needed. Communication between robots is another critical factor. They must share information about their progress, obstacles encountered, and any adjustments needed in real time. This collaborative approach allows the entire fleet of robots to work as a cohesive unit, enhancing overall efficiency. The robots must be designed to adapt to the evolving structure of the Dyson Sphere. As the sphere grows, the construction environment will change, requiring robots to modify their operations. Flexibility in their programming and physical design is essential for adapting to these new conditions. Security is an important consideration in autonomous robotic construction. The robots and their control systems must be protected from potential cyber threats or malfunctions that could disrupt the project. Ensuring the integrity of the construction process is crucial for the success of the Dyson Sphere. Robotic construction also allows for operations in areas that would be hazardous for humans. Whether it's assembling components close to the star or working in deep space, robots can operate in environments that are beyond human capabilities. This extends the range and scope of construction activities. The use of autonomous robots reduces the overall cost and time required for construction. By working around the clock, without the need for breaks, robots can accelerate the completion of the Dyson Sphere. This efficiency is crucial given the project's scale and the vast resources it requires. Ultimately, autonomous robotic construction represents the future of large-scale space projects. These robots will not only build the Dyson Sphere but also pave the way for future endeavors in space exploration and infrastructure. Their role is central to turning the ambitious concept of a Dyson Sphere into reality. Modular construction offers a flexible and scalable approach to building a Dyson Sphere. By assembling the structure in smaller, manageable sections, each module can be constructed and tested independently before being integrated into the larger framework. This method allows for easier troubleshooting and adjustments during the construction process. One of the main advantages of modular construction is the ability to adapt the design as new technologies or materials become available. If a more efficient energy collection system is developed, it can be incorporated into future modules without needing to alter the entire structure. This adaptability ensures the Dyson Sphere remains at the cutting edge of technological advancements. Modular construction also simplifies logistics. By transporting smaller components to the construction site, the challenges of moving and assembling massive structures in space are reduced. Each module can be launched and positioned with precision, minimizing the risks associated with large-scale space operations. On the other hand, continuous building focuses on constructing the Dyson Sphere as a single, unified structure. This method prioritizes a seamless integration of all parts, which can enhance structural integrity and energy efficiency. By building continuously, there's less risk of mismatches or misalignments between different sections. Continuous building is particularly advantageous when time is a critical factor. Without the need to pause for module testing or integration, the construction process can proceed at a faster pace. This approach is ideal for projects where speed is a priority, and the infrastructure for constant construction is well established. However, continuous building requires a highly coordinated effort, as all parts of the Dyson Sphere must be constructed in sync. Any delays or issues in one section can impact the entire structure. This method demands meticulous planning and real-time management to ensure the project remains on schedule. Modular construction allows for a phased approach to the Dyson Sphere's completion. Each phase can be planned according to available resources and technological capabilities, allowing for gradual expansion. This method is beneficial for projects with long timelines, where steady progress is preferred over rapid completion. In contrast, continuous building might require a larger upfront investment in resources and infrastructure. The need to maintain a constant construction pace means that all necessary materials and technologies must be available from the start. This approach can be more resource-intensive, but it can also lead to a quicker realization of the project's full potential. Modular construction supports redundancy. If one module fails or needs upgrading, it can be isolated and addressed without affecting the entire Dyson Sphere. This compartmentalized approach enhances the overall reliability and maintenance of the structure, ensuring that problems can be localized and managed effectively. Continuous building, while less flexible, can create a more cohesive and efficient structure. The lack of joints or modular connections reduces potential weak points, leading to a stronger and more durable Dyson Sphere. This seamless design can also improve the efficiency of energy transmission and distribution throughout the structure. The decision between modular construction and continuous building often depends on the specific goals and constraints of the project. Modular construction offers flexibility and adaptability, making it ideal for long-term projects with evolving requirements. Continuous building provides speed and cohesion, suited for projects where a unified structure is paramount. Modular construction is also more forgiving of technological and logistical challenges. If a particular module encounters issues, the rest of the project can continue while the problem is resolved. This approach reduces the overall risk and keeps the project moving forward, even in the face of setbacks. Continuous building requires a stable and controlled environment, where all aspects of construction can proceed without interruption. This method is best suited for scenarios where the entire project can be tightly managed, and where the benefits of a unified structure outweigh the need for flexibility. Ultimately, the choice between modular construction and continuous building shapes the entire strategy for constructing a Dyson Sphere. Each approach has its strengths and challenges, and the decision will be influenced by the project's objectives, timeline, and available resources. Both methods offer viable paths to realizing one of humanity's most ambitious engineering feats. Orbital assembly strategies are crucial for constructing a Dyson Sphere efficiently and safely. The vastness of space and the scale of the structure require precise planning and coordination to ensure that each component is placed correctly. Selecting the right strategy can determine the success of the entire project. One effective strategy is the use of assembly stations in orbit around the star. These stations act as hubs where materials are delivered, processed, and then assembled into larger sections before being integrated into the Dyson Sphere. This approach centralizes the assembly process, making it easier to manage and monitor. Robotic assembly lines are another key component of orbital strategies. These autonomous systems can operate continuously, piecing together smaller components into the larger structure. Their ability to work without human intervention speeds up the process and reduces the risk of errors during assembly. Another approach involves the deployment of prefabricated modules that are constructed off-site and then transported to the assembly area. These modules are designed to fit together seamlessly in orbit, allowing for quick and efficient construction. This method reduces the need for complex on-site manufacturing. Orbital tethers can be used to stabilize and align components during assembly. These tethers, anchored to larger structures or asteroids, help maintain the precise positioning required for the Dyson Sphere's segments. This technique ensures that components are aligned accurately as they are added to the growing structure. Careful timing and sequencing of component delivery are essential for a smooth assembly process. Components must arrive in the correct order and at the right time to prevent bottlenecks and ensure that each part of the Dyson Sphere can be assembled without delays. This requires meticulous planning and coordination across the entire project. The use of swarm robotics is another innovative strategy. Swarms of small cooperative robots can work together to assemble components in orbit. These robots can communicate and coordinate their actions, allowing them to complete complex tasks more efficiently than larger, single-purpose machines. One challenge in orbital assembly is managing the gravitational pull of the star. As the Dyson Sphere grows, its components are subjected to varying gravitational forces that can affect their stability and positioning. Strategies must account for these forces, using thrusters or tethers to maintain the correct alignment. In situ resource utilization plays a role in orbital assembly as well. By sourcing materials from asteroids or moons near the star, the need for long-distance transportation is reduced. This not only saves time but also allows for quicker responses to any material shortages or unexpected challenges. Communication between the assembly teams, both robotic and human, is critical. High-speed, low-latency communication networks are required to ensure that all parts of the assembly process are synchronized. This real-time coordination helps prevent errors and keeps the project on track. Another strategy involves assembling smaller segments in lower orbits before moving them to their final positions. This phased approach allows for easier adjustments and testing of components before they become part of the larger structure. It also provides opportunities to refine and optimize the assembly process. Safety is a top priority in orbital assembly. The vast distances and the potential for high-speed collisions require rigorous safety protocols. Redundant systems and contingency plans must be in place to address any issues that arise during the assembly process, ensuring the protection of both the structure and the workers. Orbital assembly also benefits from simulations and modeling. Before physical assembly begins, extensive simulations can identify potential challenges and optimize the assembly strategy. These models help predict how the components will behave in orbit and guide the development of effective assembly techniques. Environmental factors, such as solar radiation and space debris, must be considered in the assembly strategy. Protective measures like shielding and debris tracking systems are necessary to safeguard the assembly process. These strategies help ensure that the Dyson Sphere is built in a safe and controlled manner. Ultimately, successful orbital assembly strategies rely on a combination of advanced technology, careful planning, and precise execution. By choosing the right methods and adapting to the unique challenges of space, the construction of a Dyson Sphere can proceed smoothly, bringing humanity closer to harnessing the power of a star. Avoiding collisions and structural failures is a paramount concern in the construction of a Dyson Sphere. The vast scale and complexity of the structure make it vulnerable to various risks, so proactive measures are essential to ensure its integrity. Preventing collisions between components, as well as external objects, requires meticulous planning and continuous monitoring. One of the primary strategies for avoiding collisions is the precise tracking of all components within the Dyson Sphere. Advanced sensors and tracking systems can monitor the position and trajectory of every part, allowing for real-time adjustments. This constant vigilance helps prevent accidental impacts during assembly and operation. Collision avoidance also involves implementing strict traffic control protocols. As materials and components are moved into place, their paths must be carefully coordinated to avoid crossing or overlapping. These protocols are managed by a central AI system that ensures all movements are synchronized and free from conflict. Redundant systems play a critical role in preventing structural failures. By incorporating backup components and systems, the Dyson Sphere can continue functioning even if a primary component fails. Redundancy provides an additional layer of security, ensuring that the structure remains stable and operational under various conditions. The use of shock absorbers and dampening mechanisms is essential for reducing the impact of any collisions that do occur. These systems can absorb the energy of an impact, preventing it from spreading through the structure and causing further damage. By localizing the effects, the overall integrity of the Dyson Sphere is preserved. Structural integrity is also maintained through the use of high-strength materials. The components of the Dyson Sphere must be made from materials that can withstand the stresses of space, including micrometeoroid impacts, thermal expansion, and gravitational forces. Using advanced alloys and composites helps ensure that the structure remains robust. Another critical aspect is the regular inspection and maintenance of the Dyson Sphere. Automated systems can continuously monitor the condition of the structure, identifying any weaknesses or signs of wear. Early detection of potential issues allows for timely repairs, preventing minor problems from escalating into major failures. In some cases, modular design contributes to avoiding large-scale structural failures. If one part of the Dyson Sphere experiences a failure, it can be isolated and addressed without affecting the rest of the structure. This compartmentalization reduces the risk of a single failure compromising the entire system. Environmental hazards, such as solar radiation and space debris, must also be mitigated to avoid structural failures. Protective shielding and debris deflection systems are essential for safeguarding the Dyson Sphere against these external threats. These measures ensure that the structure remains intact, despite the harsh conditions of space. Dynamic stress testing is another important tool in avoiding structural failures. By simulating various conditions and loads, engineers can predict how the Dyson Sphere will respond to different scenarios. This testing allows for the identification and reinforcement of potential weak points before they become critical. Avoiding collisions also requires careful consideration of the Dyson Sphere's internal layout. The placement of components, energy conduits, and other infrastructure must be planned to minimize the risk of interaction. Proper spacing and alignment reduce the chances of accidental contact between parts. Emergency response systems are critical for addressing any unforeseen collisions or failures. These systems can automatically initiate corrective actions, such as rerouting power, sealing off damaged areas, or deploying repair bots. Quick response capabilities are vital for minimizing damage and restoring normal operations. The integration of artificial intelligence in managing collision avoidance and structural integrity is essential. AI systems can analyze data in real time, predict potential risks, and make decisions to avert crises. Their ability to process vast amounts of information quickly is crucial for maintaining the safety of the Dyson Sphere. Training and simulations for human operators and AI systems alike ensure that all parties involved are prepared to handle emergencies. Regular drills and scenario planning help develop effective responses to potential failures, ensuring that the Dyson Sphere can recover quickly from any incidents. Ultimately, avoiding collisions and structural failures is about maintaining a balance between proactive design, real-time monitoring, and effective response strategies. By combining these elements, the Dyson Sphere can be constructed and operated safely, harnessing the power of a star without compromising its structural integrity. Maintenance and repairs in space are critical to the long-term success of a Dyson Sphere. The harsh environment of space, with its extremes of temperature, radiation, and micrometeoroid impacts, makes regular upkeep essential. Without a robust maintenance strategy, even the most advanced structures can degrade over time. One of the key challenges of maintenance in space is the distance from Earth. Sending human crews for repairs is time-consuming and costly, so autonomous systems must be the primary method for addressing issues. These systems include repair drones and robotic arms, which can perform tasks ranging from minor adjustments to significant repairs. Routine inspections are vital to identifying potential problems before they become critical. Sensors embedded throughout the Dyson Sphere continuously monitor for signs of wear, damage, or system malfunctions. These sensors provide real-time data, enabling preemptive action to be taken before failures occur. Self-repairing materials are another innovation that can significantly reduce the need for manual maintenance. These materials are designed to heal minor damages on their own, such as sealing small cracks or holes caused by micrometeoroids. This capability ensures that the Dyson Sphere can maintain its integrity without constant human intervention. For larger repairs, modular design offers a practical solution. Components of the Dyson Sphere are designed to be easily replaced, allowing damaged sections to be swapped out with minimal disruption. This modularity speeds up the repair process and helps ensure that the Dyson Sphere remains fully operational. Maintenance in space also involves managing the buildup of space debris on the Dyson Sphere's surface. Accumulated dust and debris can reduce the efficiency of energy collection systems. Regular cleaning operations, potentially performed by specialized robots, are necessary to keep the panels and other surfaces clear. Energy management during repairs is another important consideration. Systems must be designed to reroute power around sections that are undergoing maintenance, ensuring that the Dyson Sphere continues to function even when parts of it are offline. This redundancy is crucial for maintaining a consistent energy output. The timing of maintenance activities must be carefully planned to avoid interference with the Dyson Sphere's normal operations. Scheduling repairs during periods of lower energy demand can help minimize the impact on overall performance. This strategic planning is essential for balancing maintenance needs with energy production goals. Communication between maintenance systems is critical for coordinating repairs. Autonomous units must be able to share data and work together to address issues efficiently. A centralized control system oversees these operations, ensuring that all maintenance activities are aligned and effective. Space weather poses additional challenges for maintenance. Solar storms and other cosmic events can temporarily disrupt repair activities or cause additional damage. Maintenance systems must be resilient and adaptable, capable of responding to these unpredictable conditions while safeguarding the Dyson Sphere. Logistics also play a significant role in space maintenance. Replacement parts, tools, and other resources must be stored strategically within the Dyson Sphere to ensure quick access when needed. Efficient supply chain management in space is vital for reducing downtime and keeping the structure in optimal condition. The durability of maintenance systems themselves is a key consideration. Repair robots and drones must be built to last, capable of operating for extended periods without requiring significant repairs or replacements themselves. This self-sufficiency is crucial for long-term sustainability in the remote environment of space. Training and simulation for maintenance personnel, even if they operate remotely, are essential for preparing for potential challenges. Understanding the complexities of the Dyson Sphere and its systems allows for quicker, more effective responses when issues arise. Continuous learning and adaptation are vital to maintaining the structure's integrity. Innovations in maintenance technologies will continue to evolve alongside the Dyson Sphere. As new challenges emerge, maintenance strategies must be flexible and forward-thinking, incorporating the latest advancements in robotics, materials science, and space operations. This continuous improvement ensures the Dyson Sphere remains viable for generations. In the end, successful maintenance and repairs in space require a combination of advanced technology, strategic planning, and continuous vigilance. By integrating these elements, the Dyson Sphere can operate reliably and efficiently, fulfilling its purpose as a monumental source of energy for the future. Dyson swarms offer a flexible approach to harnessing stellar energy by deploying a large number of individual satellites rather than a single continuous structure. One of the main advantages is scalability. A swarm can be expanded gradually, adding more satellites over time as resources allow. This makes it easier to start small and grow as needed. The modular nature of Dyson swarms also provides resilience. If one satellite fails, it doesn't significantly impact the overall system, which can continue functioning without interruption. This redundancy reduces the risk of catastrophic failure compared to a single monolithic structure. Another benefit is the ease of repair and replacement. Individual satellites can be serviced or replaced without affecting the entire swarm. This modular approach simplifies maintenance and allows for continuous upgrades as technology advances. However, managing a Dyson swarm poses significant challenges in coordination. Each satellite must maintain its precise orbit to avoid collisions and ensure optimal energy capture. This requires sophisticated control systems and constant monitoring, increasing the complexity of the project. The energy transmission from a Dyson swarm is another consideration. With many separate collectors, Efficient energy transfer to a central location or multiple destinations becomes more complex. This can lead to inefficiencies and requires advanced technologies to manage the distribution effectively. Dyson swarms are also more adaptable to different star types and environmental conditions. The satellites can be designed to suit specific needs and adjusted based on the star's characteristics or changes in energy demand. This adaptability makes Dyson swarms a versatile solution for various scenarios. On the downside, the initial setup for a Dyson swarm can be resource-intensive. Even though it can be scaled up over time, the deployment of the first satellites requires significant investment in technology and materials. This upfront cost can be a barrier to starting the project. The vast area covered by a Dyson swarm increases its vulnerability to space debris and micrometeoroids. Protecting each satellite from these hazards adds to the complexity and cost of the system. The need for ongoing protection and repair is higher than in more consolidated structures. Despite these challenges, Dyson swarms offer a high degree of flexibility and energy capture. Satellites can be positioned to maximize exposure to the star's energy output, even as the star's activity changes over time. This adaptability ensures consistent energy production. Another con is the potential for interference with other space operations. The large number of satellites orbiting the star could complicate navigation for spacecraft and other missions in the same region. This requires careful coordination and possibly international agreements to manage. Dyson swarms also require advanced communication systems to keep all satellites synchronized. The need for real-time data exchange between satellites and control centers increases the demand for robust, high-speed communication networks. This infrastructure is essential but adds to the complexity of the project. On the environmental side, Dyson swarms have a lower impact on the star's system compared to a solid Dyson shell. The open nature of the swarm allows more natural light and heat to escape, potentially reducing the impact on nearby planets or other celestial bodies. This makes Dyson swarms a more environmentally sustainable option. However, the decentralized nature of a Dyson swarm can lead to uneven energy distribution. If satellites are not perfectly aligned or if some fail, the energy collected can vary, leading to inefficiencies in overall power generation. Ensuring a consistent energy output requires meticulous planning and constant adjustments. In summary, Dyson swarms offer a balance of flexibility, scalability, and resilience, making them an attractive option for harnessing stellar energy. Yet they come with significant challenges in coordination, communication, and maintenance. Weighing these pros and cons is essential in deciding whether a Dyson swarm is the right approach for a particular energy project. The structural integrity of a Dyson shell is a critical factor in its design and feasibility. Unlike a Dyson swarm, a shell aims to be a continuous solid structure encircling a star, which presents immense engineering challenges. The sheer size of the shell means it must be incredibly strong to maintain its shape and withstand various stresses. One of the primary concerns is the immense gravitational forces exerted by the star at the center of the shell. These forces could cause the shell to collapse inward if not properly balanced by centrifugal forces or other engineering solutions. Achieving this balance is essential for the shell's stability. The materials used in constructing a Dyson shell must be both lightweight and incredibly strong. Advanced composites or materials with high tensile strength are necessary to support the shell's structure without adding excessive mass. This choice of materials directly impacts the shell's durability and longevity. Thermal expansion is another significant issue. The Dyson shell will be exposed to extreme temperatures, both from the star's radiation and the cold of space. As the structure heats and cools, it will expand and contract, potentially causing stress fractures or warping if not carefully managed. To address thermal stresses, the shell's design might include flexible joints or segments that allow for controlled expansion and contraction. This flexibility helps prevent the buildup of stress in any one area, reducing the risk of structural failure over time. Such designs are crucial for maintaining the shell's integrity. The internal pressure within the Dyson shell must also be managed carefully. If the shell is designed to hold an atmosphere or other internal environments, this pressure adds an additional layer of complexity to its structural design. Ensuring the shell can withstand this pressure without compromising its structural integrity is essential. Another challenge is the potential for micrometeoroid impacts. Even small particles traveling at high speeds can cause significant damage to the shell. Incorporating protective shielding and self-repairing materials can help mitigate these risks, but they add to the complexity of the design. The sheer scale of a Dyson shell means that any structural issues could have catastrophic consequences. A failure in one part of the shell could lead to a chain reaction, compromising the entire structure. Redundancy and fail-safes must be built into the design to prevent localized failures from spreading. Energy distribution within the Dyson shell also impacts its structural integrity. The shell must be designed to evenly distribute the energy it collects, preventing hotspots or areas of excessive stress. This balance is crucial to avoiding structural weaknesses over time. Maintaining the shell's shape and alignment is another critical concern. The forces acting on the shell are not uniform, and slight misalignments could lead to uneven stress distribution. Continuous monitoring and adjustment systems are necessary to keep the shell properly aligned and structurally sound. The Dyson shell must also account for external forces, such as gravitational interactions with other celestial bodies. These forces could cause the shell to drift or deform over time, if not properly countered. The design must include mechanisms to stabilize the shell against these external influences. Constructing the shell in segments or modules can help manage its structural integrity. By building the shell in smaller, interconnected pieces, the overall structure becomes more resilient to individual failures. This modular approach also simplifies repairs and upgrades. Redundancy in structural supports is vital for the Dyson shell's durability. Multiple layers of reinforcement or backup systems can help ensure that the shell remains intact, even if one layer fails. This redundancy is a key element in designing a structure that can endure for millennia. The Dyson shell must also be designed to manage the immense energy it captures. Without proper heat dissipation and energy management systems, the shell could overheat, leading to structural degradation. Efficient thermal management is essential for maintaining the shell's long-term stability. In conclusion, the structural integrity of a Dyson shell is a complex challenge that requires careful consideration of materials, design, and environmental factors. Achieving this integrity is crucial for the success of the Dyson shell, ensuring it can harness the energy of a star while remaining stable and secure. Comparing the resource requirements of a Dyson swarm versus a Dyson shell reveals significant differences in scale and complexity. A Dyson swarm composed of numerous individual satellites requires a steady but manageable supply of materials over time. Each satellite can be constructed, launched, and maintained independently, spreading out the resource demands. In contrast, a Dyson shell demands an immense quantity of materials from the outset. The sheer size of the shell, designed to encompass an entire star, means that the total volume of resources needed is far greater. This requirement includes not only the structural materials, but also the systems for energy collection, distribution, and maintenance. The type of materials required also differs between the two concepts. A Dyson swarm can be built with a variety of materials depending on the specific design of each satellite. This flexibility allows for the use of less expensive or more readily available resources. A Dyson shell, however, must be constructed from ultra-strong, lightweight materials that can withstand the stresses of space and the star's gravitational pull. Mining and transportation logistics play a crucial role in both scenarios. A Dyson swarm allows for the gradual extraction and use of resources, reducing the strain on any single source. The Dyson shell, on the other hand, would require the simultaneous extraction and transport of vast quantities of materials, necessitating a highly coordinated effort. The energy required for construction is another point of comparison. Building a Dyson swarm can be done in phases, with each satellite contributing to the energy supply as soon as it is operational. This phased approach helps offset the energy costs of further construction. Conversely, constructing a Dyson shell is an all-or-nothing endeavor, requiring a massive initial energy investment before it begins to pay off. Repair and maintenance resources are also distributed differently. A Dyson swarm needs a steady supply of materials for ongoing repairs and upgrades, but these demands are spread out over time and space. A Dyson shell would require a vast stockpile of resources dedicated to ensuring its continuous structural integrity, potentially making maintenance a more daunting task. The economic implications of these resource requirements are substantial. A Dyson swarm's gradual resource use allows for more flexibility in budgeting and financing, as the project can scale with available funds. In contrast, the Dyson shell's enormous upfront costs could strain even the most robust economies, requiring unprecedented levels of investment and cooperation. In terms of resource utilization, a Dyson swarm can more easily adapt to the availability of local materials, such as those found on asteroids or moons within the star system. This adaptability can reduce the need for long-distance resource transport. The Dyson shell, however, may require the import of rare or specialized materials from distant sources, further complicating logistics. The environmental impact of resource extraction also varies. A Dyson swarm, with its distributed nature, may allow for more sustainable mining practices, minimizing the disruption to any single celestial body. A Dyson shell's massive material demands could lead to the depletion of resources on multiple planets or moons, raising ethical and environmental concerns. Labor requirements differ significantly as well. A Dyson swarm benefits from automation and the use of modular, repeatable designs, reducing the need for human intervention. A Dyson shell, due to its complexity and scale, might require more specialized labor for construction, maintenance, and operation, increasing the overall resource expenditure. The timescale for resource acquisition also impacts the two approaches. A Dyson swarm can be built over an extended period, allowing for the gradual accumulation of necessary materials. The Dyson shell's resource requirements demand a rapid and sustained effort to gather and process materials, potentially accelerating resource depletion. The geopolitical implications of resource distribution must be considered. The gradual, scalable nature of a Dyson swarm allows for resource sharing and collaboration among multiple entities. A Dyson shell's concentrated resource demands could lead to competition or conflict over access to the needed materials. Waste management is another factor in resource comparison. The ongoing production and replacement of satellites in a Dyson swarm create a continuous flow of waste materials, requiring efficient recycling systems. The Dyson shell, while producing less waste overall, may generate significant amounts during its construction phase, necessitating large-scale recycling efforts. The overall sustainability of each approach depends on how resources are managed. A Dyson swarm's modular construction and distributed resource use may offer a more sustainable long-term strategy. In contrast, the Dyson shell's massive resource requirements and environmental impact could pose significant sustainability challenges. Ultimately, the resource requirements of a Dyson swarm versus a Dyson shell highlight the trade-offs between flexibility, scalability, and the immense scale of a single unified structure. Each approach demands careful consideration of the resources available, the environmental impact, and the long-term sustainability of the project. Flexibility is a key advantage of the Dyson swarm approach. The ability to deploy satellites incrementally allows for continuous adaptation to technological advancements and changing energy needs. This modularity ensures that the system can evolve over time, incorporating new innovations as they become available. Scalability is another strength of the Dyson swarm. Starting with a smaller number of satellites, the swarm can expand gradually, with each new satellite adding to the overall energy capture. This makes the project manageable, even with limited initial resources, and allows it to grow as more resources become accessible. In contrast, a Dyson shell is far less flexible. Once the design is set, altering the structure or integrating new technologies becomes extremely difficult. The shell's rigid, monolithic nature limits the ability to adapt to unforeseen challenges or opportunities, making it a less versatile solution in the long run. However, the Dyson shell offers a different kind of scalability, one that aims for a single massive leap in energy collection once completed. This all-or-nothing approach, while risky, could result in an unparalleled energy supply if successfully constructed. The shell's scale, though daunting, promises a more unified and powerful structure. The incremental nature of a Dyson swarm also allows for testing and refinement. Early satellites can be prototypes, serving as proofs of concept before full-scale deployment begins. This iterative process reduces the risk of large-scale failures and ensures that each step forward is based on proven technology. On the other hand, the Dyson shell requires absolute confidence in the design from the outset. The scale and cost of construction leave little room for error or testing. This lack of flexibility can lead to greater risk, as any unforeseen issues may only become apparent after significant resources have already been committed. The flexibility of a Dyson swarm extends to its operational capabilities. Satellites can be repositioned or even repurposed as needed, responding to shifts in energy demand or changes in the star's behavior. This adaptability is crucial for maintaining efficiency and effectiveness over the long term. Scalability in a Dyson swarm also means that energy production can begin almost immediately. As soon as the first satellites are operational, they start contributing to the energy grid. This provides an early return on investment and helps fund further expansion, creating a self-sustaining growth model. In contrast, the Dyson shell requires full completion before any energy can be harvested. This makes the shell a much longer-term investment, with no return until the entire structure is in place. The delay in energy production is a significant drawback, especially if the project encounters delays or setbacks. The decentralized nature of a Dyson swarm also enhances its resilience. If one part of the swarm fails, the rest can continue to function, minimizing the impact on overall energy production. This redundancy is a critical feature, ensuring that the system remains operational even in the face of individual component failures. Flexibility also extends to the resources used in a Dyson swarm. Different materials and technologies can be employed across various satellites, allowing for the use of locally available resources or the latest technological developments. This resource diversity helps mitigate supply chain issues and lowers costs. However, the Dyson shell's lack of flexibility could be seen as a strength in terms of uniformity and efficiency. A single, cohesive structure eliminates the complexities of managing thousands of individual satellites, potentially leading to greater overall efficiency once operational. The shell's unified design could streamline energy collection and distribution. Scalability in a Dyson swarm also supports a more collaborative approach. Multiple entities can contribute satellites to the swarm, fostering international cooperation and shared benefits. This collaborative potential makes the Dyson swarm an attractive option for global energy solutions. Yet, the Dyson shell's monolithic nature requires a centralized approach, often under a single entity or coalition. While this centralization can lead to more streamlined decision-making, it also concentrates risks and requires a level of coordination that may be challenging to achieve on a global scale. Ultimately, the choice between flexibility and scalability in a Dyson swarm versus the rigid, all-encompassing nature of a Dyson shell reflects different priorities and risk tolerances. Each approach has its merits, and the decision will depend on the specific goals, resources, and timelines of the civilization undertaking the project. Future expansion possibilities are a vital consideration when designing a Dyson sphere, particularly for a Dyson swarm. The modular nature of a swarm makes it inherently expandable, allowing for the continuous addition of new satellites as technology advances or energy demands increase. This flexibility ensures that the Dyson swarm can evolve to meet the needs of future generations. The addition of specialized satellites tailored to different energy collection methods is one potential avenue for expansion. As new technologies emerge, such as more efficient photovoltaic cells or advanced energy storage systems, these can be integrated into the existing swarm. This adaptability allows the Dyson swarm to remain at the forefront of energy production. Expansion could also involve extending the swarm beyond a single star. As interstellar travel becomes more feasible, building additional swarms around neighboring stars could create a vast, interconnected energy network. This would not only increase total energy output but also provide redundancy, safeguarding against potential failures in any single system. For a Dyson shell, expansion possibilities are more limited due to its rigid structure. However, upgrades and enhancements are still possible. As new materials and technologies become available, sections of the shell could be retrofitted or replaced, improving efficiency or durability. This approach allows for some degree of technological progression within the shell's framework. The construction of additional Dyson shells around other stars is another expansion possibility. While each shell is a massive undertaking, a network of shells could eventually provide energy on an unprecedented scale. This would require significant advancements in interstellar construction and resource extraction. Expansion might also include the development of habitats within the Dyson sphere structure itself. For a Dyson swarm, this could mean integrating living modules into some of the satellites, creating space habitats that are powered directly by the star's energy. These habitats could support large populations, effectively turning the Dyson swarm into a self-sustaining ecosystem. In the context of a Dyson shell, internal habitats could be constructed on the inside surface of the shell. These environments would have access to constant controlled energy, making them ideal for sustaining life. The shell could house entire civilizations, turning it into more than just an energy-collecting structure. Another expansion possibility involves using the Dyson Sphere as a base for launching deep space exploration missions. With an abundant energy supply, it could power advanced propulsion systems, making interstellar travel more practical. This would transform the Dyson Sphere from an energy source into a hub for space exploration. The development of energy transmission networks that extend across star systems could also be a future expansion. Using laser or microwave technology, the energy harvested by the Dyson Sphere could be transmitted to distant locations, supporting colonies or space stations far from the original star. This would create a vast, interconnected energy grid across space. For a Dyson swarm, the modular nature allows for easy incorporation of new scientific instruments or communication arrays. As technology advances, these satellites could be upgraded to perform new functions, such as deep space communication or astronomical observations, turning the Dyson swarm into a multifunctional tool for exploration and research. Future expansion might also include the development of artificial intelligence systems that manage the Dyson Sphere's operations autonomously. These AI systems could optimize energy collection, distribution, and maintenance, ensuring that the Dyson Sphere operates at peak efficiency even as it grows. The expansion of the Dyson Sphere could also involve the use of it as a platform for large-scale experiments or production facilities. The immense energy available could be harnessed for purposes beyond mere power generation, such as the production of antimatter or the operation of particle accelerators on an unprecedented scale. As humanity's technological capabilities continue to grow, the Dyson Sphere could serve as the foundation for even more ambitious megastructures. Concepts like the Matryoshka brain, a theoretical supercomputer powered by a Dyson Sphere, could become feasible, using the vast energy supply to perform computations at levels unimaginable today. Expansion could also be driven by the need to accommodate growing energy demands. As civilizations expand, so too does their energy consumption. The Dyson Sphere, particularly a Dyson swarm, could be scaled up to meet these demands, ensuring a stable and continuous energy supply for millennia. Ultimately, the future expansion possibilities of a Dyson Sphere are limited only by our imagination and technological progress. Whether through the addition of new satellites, the construction of additional shells, or the integration of advanced technologies, the Dyson Sphere offers a platform for continuous growth and evolution, shaping the future of energy and space exploration. An unlimited energy supply from a Dyson Sphere could transform every aspect of human life. With no constraints on power, industries could operate at full capacity, leading to an era of unprecedented production and innovation. The concept of energy scarcity would become obsolete, reshaping economies and societies. In such a world, the barriers to technological advancement would be significantly lowered. Energy-intensive projects, once deemed impossible or too costly, could be pursued freely. This might lead to breakthroughs in areas like space colonization, artificial intelligence, and advanced manufacturing. The elimination of energy shortages could also help resolve many global challenges. Access to unlimited power could enable the widespread adoption of desalination plants, providing fresh water in even the driest regions. Similarly, food production could be revolutionized, with energy-intensive farming techniques making hunger a thing of the past. However, the prospect of unlimited energy raises questions about sustainability. With no need to conserve power, humanity might adopt wasteful practices, leading to environmental degradation. The challenge will be to balance abundant energy with responsible consumption to avoid new forms of ecological damage. An unlimited energy supply could also reshape global politics. Energy resources, which have long been a source of conflict, would no longer be a point of contention. This could lead to greater international cooperation, or, conversely, new power struggles over who controls this vast resource. The potential for economic inequality remains a concern. While some regions might flourish with access to unlimited energy, others could be left behind if they lack the infrastructure to harness and distribute this power effectively. Ensuring that the benefits of unlimited energy are shared globally will be crucial. On a societal level, unlimited energy could lead to significant changes in lifestyle. The convenience and comfort afforded by limitless power could alter human behavior, potentially reducing the need for physical labor, or even altering social structures. This might create new opportunities for leisure and creativity, but it could also lead to societal stagnation. The environmental impact of unlimited energy must also be considered. While it could reduce reliance on fossil fuels, the increased use of energy might lead to other environmental issues, such as heat pollution, or the strain on natural resources required to build and maintain the energy infrastructure. In the realm of space exploration, unlimited energy opens up new possibilities. Interstellar travel, once a distant dream, could become a reality. The power to send spacecraft to distant stars or even terraform other planets would no longer be limited by energy constraints, expanding humanity's reach in the cosmos. The development of new technologies would likely accelerate in an era of unlimited energy. From quantum computing to nanotechnology, the possibilities are vast. However, this rapid advancement could also outpace our ability to understand and manage these technologies responsibly. Unlimited energy could also have profound effects on the cultural and artistic expressions of humanity. With energy no longer a limiting factor, artists and creators could explore new mediums and forms of expression, potentially leading to a renaissance of creativity and innovation. The potential for global infrastructure projects would expand dramatically. Megastructures, floating cities, and even artificial planets could become feasible with the power of a Dyson Sphere. These projects could redefine the human experience, creating new environments and ways of living. In education, unlimited energy could make learning more accessible and immersive. Virtual reality, advanced simulations, and other energy-intensive technologies could become standard, offering students unprecedented ways to explore and understand the world. The ethical implications of unlimited energy are significant. With such power, humanity will need to consider how it is used and who benefits from it. The potential for misuse or inequality is high, and careful governance will be necessary to ensure that this resource is used for the common good. Ultimately, the arrival of unlimited energy would mark a new chapter in human history. It offers the potential for boundless growth and innovation, but also poses challenges that will require careful thought and responsible action. The future shaped by this energy will depend on the choices we make and the values we uphold as we move forward. Supporting interstellar exploration with the energy harnessed from a Dyson Sphere could revolutionize humanity's ability to reach distant stars. With virtually limitless power at our disposal, the technological and logistical challenges of interstellar travel could be overcome, opening up new frontiers for exploration. The energy provided by a Dyson Sphere could power advanced propulsion systems, such as nuclear fusion or antimatter engines. These systems, which require immense amounts of energy, could drastically reduce travel times between stars, making journeys that once took centuries possible within a single human lifetime. This abundant energy could also support the development of large-scale spacecraft capable of carrying entire communities. These interstellar vessels, powered by the Dyson Sphere, could be self-sustaining, with the ability to produce their own food, water, and energy, enabling long-duration missions far from Earth. Communication across vast interstellar distances could also benefit from the energy generated by a Dyson Sphere. High-powered lasers or other advanced communication systems could maintain real-time contact between Earth and distant colonies, ensuring that explorers remain connected with their home planet. Energy-intensive terraforming projects on distant planets could become feasible with the support of a Dyson Sphere. Transforming barren worlds into habitable environments would require vast resources, but with unlimited energy, these ambitious projects could become a reality, expanding humanity's presence across the galaxy. The construction of deep space infrastructure, such as relay stations or refueling depots, would be critical for supporting interstellar missions. The energy from a Dyson Sphere could power these facilities, ensuring that spacecraft have the resources they need to continue their journeys across the stars. A Dyson Sphere could also support the creation of advanced research stations in space. These stations could study the effects of long-term space travel on humans, test new technologies, and conduct experiments that are only possible in the unique conditions of deep space, further advancing our understanding of the universe. Interstellar exploration would require a robust logistical network, capable of supplying missions with everything from spare parts to medical supplies. The energy from a Dyson Sphere could power autonomous drones or AI-managed logistics systems, ensuring that supplies are efficiently delivered across the vast distances of space. The potential to discover and interact with other intelligent civilizations could be significantly enhanced by a Dyson Sphere. With the ability to travel and communicate across interstellar distances, humanity could explore new cultures, exchange knowledge, and perhaps even establish alliances with extraterrestrial beings. The Dyson Sphere could also support the development of defensive systems to protect interstellar missions from potential threats, whether they come from space debris, hostile environments, or even other civilizations. These defenses would be powered by the sphere's abundant energy, ensuring the safety of explorers. Exploration of exoplanets, distant moons, and other celestial bodies would become far more feasible. The energy from the Dyson Sphere could power detailed surveys, robotic missions, and even manned expeditions to study these worlds, expanding our knowledge of the galaxy's diversity. Long-term colonization efforts could be supported by the continuous energy supply from a Dyson Sphere. Establishing permanent settlements on distant planets would require a stable and abundant source of power, which the sphere could provide, enabling humanity to thrive in new environments. The potential for interstellar trade could be unlocked with the energy from a Dyson Sphere. Transporting goods, knowledge, and resources across the galaxy would become economically viable, fostering new interstellar economies and connections between distant colonies and Earth. The Dyson Sphere could also enable the construction of massive space habitats where humans could live and work while traveling between stars. These habitats, powered by the sphere's energy, could serve as waypoints or even independent colonies in their own right, supporting the expansion of human civilization. In the long run, the energy from a Dyson Sphere could be the key to humanity's transformation into a truly interstellar species. By providing the power needed to explore, colonize, and thrive in distant star systems, the Dyson Sphere would open up the universe to human ambition and ingenuity, setting the stage for the next great era of exploration. Powering massive computational projects with the energy from a Dyson Sphere could push the boundaries of what is technologically possible. With virtually unlimited energy, we could run simulations and calculations that were once thought unimaginable, advancing fields like climate modeling, quantum computing, and artificial intelligence. This energy could fuel the creation of a global, or even interstellar, computational network, where immense processing power is distributed across the galaxy. Such a network could tackle the most complex problems, from decoding the mysteries of the universe to predicting future societal trends with unparalleled accuracy. Quantum computing, which requires significant energy to maintain quantum states, could be fully realized with the support of a Dyson Sphere. These quantum computers could solve problems in seconds that would take classical computers millennia, revolutionizing industries like cryptography, drug discovery, and materials science. Massive data centers powered by Dyson Sphere energy could store and process the vast amounts of data generated by a highly connected, advanced civilization. These centers could enable real-time processing of global information, facilitating everything from financial markets to global communication networks. Artificial intelligence could reach new heights with the energy from a Dyson Sphere. Advanced AI systems, requiring vast computational resources to simulate human cognition or process large datasets, could operate at levels beyond current capabilities. This could lead to AI systems that surpass human intelligence and creativity. The energy could also support the creation of a virtual reality infrastructure on a scale never before seen. Entire digital worlds, complex simulations, and immersive experiences could be powered continuously, offering new ways for humans to interact, learn, and entertain themselves. Modeling and simulation projects that require intense computational power, such as simulating the weather patterns of entire planets or the dynamics of galaxies, would become feasible. These simulations could provide insights into phenomena that are currently beyond our understanding. Energy-intensive tasks like genetic analysis or the simulation of biological systems could be performed at unprecedented scales. This could accelerate the development of personalized medicine, new therapies, and a deeper understanding of life itself. The energy from a Dyson Sphere could enable the construction and operation of the Matryoshka brain, a theoretical megastructure that functions as a giant supercomputer. This structure could host consciousness uploads, simulate entire universes, or perform calculations of such complexity that they redefine our understanding of intelligence. With access to vast computational resources, humanity could undertake projects like simulating entire economies or global ecosystems in real time. These simulations could help us manage resources more effectively, predict economic trends, or address environmental challenges with greater precision. The ability to power continuous, massive-scale machine learning projects could revolutionize the development of AI. Machines could learn and adapt in real time, leading to autonomous systems that can operate independently and improve themselves without human intervention. Global communication systems could be enhanced by the energy from a Dyson Sphere, supporting instantaneous, high-bandwidth communication across interstellar distances. This would not only keep humanity connected across the stars, but also allow for the continuous exchange of data and information on an unprecedented scale. The energy could support the operation of large-scale encryption and security systems, ensuring that data and communication remain secure in a highly connected digital universe. These systems could protect against cyber threats and maintain the integrity of global networks. Advanced scientific research, such as particle physics experiments or astrophysical observations, often requires enormous amounts of energy. The Dyson Sphere could power experiments that probe the fundamental nature of reality, uncovering new laws of physics or validating theories that were previously impossible to test. In summary, the energy from a Dyson Sphere could unlock computational capabilities that redefine what is possible for human civilization. From AI and quantum computing to virtual realities and global simulations, this energy could fuel the next great leap forward in technology, pushing the boundaries of knowledge and capability. The energy from a Dyson Sphere could catalyze unprecedented advancements in science and technology. With such a vast power source, researchers could push the boundaries of what is known and explore realms that were previously beyond reach. This abundance of energy would accelerate innovation across multiple disciplines. In the field of physics, the ability to power large-scale experiments could lead to the discovery of new particles or forces, deepening our understanding of the universe. High-energy particle colliders, powered by a Dyson Sphere, could probe the very fabric of space-time, revealing secrets about the origins of the cosmos. Biotechnology could see remarkable progress as well. Unlimited energy could support the development of advanced genetic engineering techniques, allowing for the creation of new life forms or the enhancement of human capabilities. These innovations could revolutionize medicine and extend human lifespans. And material science would benefit immensely from the energy available. Researchers could experiment with new materials at atomic scales, developing substances with unprecedented strength, flexibility, or conductivity. These materials could be used in everything from spacecraft to everyday consumer products. In space exploration, the energy from a Dyson Sphere could power missions to the most distant corners of the galaxy. With no energy limitations, humanity could send probes, landers, and crewed missions to explore other star systems, expanding our knowledge of the universe and our place within it. Advanced manufacturing techniques, such as molecular assemblers or 3D printing at a molecular level, could become commonplace. These technologies could produce anything from complex machinery to biological tissues, transforming industries and making manufacturing more efficient and sustainable. And the energy could also support the development of new propulsion technologies. Concepts like warp drives or wormholes, which currently exist only in theory, might become feasible. These advancements could make faster-than-light travel a reality, opening the door to exploring new galaxies. Nanotechnology would flourish with the resources provided by a Dyson Sphere. Nanoscale machines could be developed to perform tasks at the cellular or molecular level, such as repairing tissues, cleaning the environment, or assembling new materials atom by atom. Artificial intelligence and robotics could advance at an exponential rate. With the energy to power massive AI systems, robots could become more autonomous, intelligent, and capable of performing complex tasks without human intervention. This could lead to a new era of automation in every sector. In the field of medicine, the ability to run complex simulations and analyze vast amounts of data could lead to breakthroughs in understanding diseases, developing new treatments, and even finding cures for conditions that are currently incurable. Personalized medicine could become the standard. Environmental technology could also advance rapidly. With the power to drive large-scale environmental restoration projects, humanity could reverse damage caused by climate change, clean up pollution, and restore ecosystems. This could lead to a more sustainable and balanced relationship with the planet. Communication technologies could evolve to new heights. With the ability to transmit data across vast distances almost instantaneously, humanity could maintain constant contact across planets and star systems. This would strengthen our ability to collaborate and share knowledge across the galaxy. The study of consciousness could benefit from the energy provided by a Dyson Sphere. Researchers could explore the nature of consciousness, potentially leading to the development of technologies that interface directly with the human mind, enhancing cognitive abilities or allowing for mind-to-mind communication. Education would be transformed by the advancements supported by a Dyson Sphere. With access to unlimited information and immersive technologies like virtual reality, learning could become more interactive, personalized, and accessible to people everywhere, breaking down barriers to education. In summary, the energy from a Dyson Sphere would be a catalyst for a new era of scientific and technological advancement. The possibilities are as vast as the energy source itself, with potential breakthroughs that could redefine every aspect of human life and push the boundaries of what we can achieve. The societal transformations brought about by the energy from a Dyson Sphere could be profound. With access to unlimited energy, social structures might shift, leading to new forms of governance, economic systems, and ways of life. The abundance of resources could reduce or even eliminate poverty, reshaping societies around the world. We might see a drastic reduction in global inequality. As energy becomes plentiful and cheap, the gap between rich and poor nations could narrow, allowing for a more equitable distribution of wealth and resources. This could foster a more unified global community, where the focus shifts from competition to collaboration. The concept of work could change dramatically. With machines and AI handling most energy-intensive and laborious tasks, humans could focus on creative, intellectual, and leisure activities. This shift could lead to a society where work is no longer a necessity but a choice, fundamentally altering the nature of human life. Urbanization patterns might also change. With abundant energy, the need for centralized cities could diminish. People might choose to live in more remote or customized environments, supported by advanced infrastructure and technology that make any location livable and connected. Education could become universally accessible, as the resources needed to provide high-quality learning would no longer be constrained by energy or funding. This democratization of knowledge could empower individuals everywhere, leading to a more informed and capable global population. Healthcare systems could be revolutionized, with energy-intensive treatments and technologies becoming widely available. Universal healthcare might become a reality, supported by the abundance of resources. Lifespan could increase, and quality of life could improve across all demographics. Cultural expressions might flourish in new ways. With more time and resources available, people could engage more deeply in the arts, philosophy, and sciences. This could lead to a renaissance of creativity, where culture evolves rapidly and becomes more diverse and inclusive. Governments might need to evolve to manage the changes brought by unlimited energy. Traditional power structures could be challenged as new forms of governance emerge, focused on managing resources, technology, and the social changes that come with them. This could lead to more decentralized or participatory forms of government. The relationship between humans and nature could be redefined. With the ability to repair environmental damage and sustainably manage resources, humanity could enter a new era of environmental stewardship. This could lead to a more harmonious coexistence with the natural world. Social norms and values could shift as well. With energy abundance, the importance of material wealth might diminish, leading to a society that values knowledge, creativity, and personal fulfillment over economic status. This could result in a more holistic approach to human development. The structure of families and communities might also evolve. With the pressures of survival reduced, people might choose to form communities based on shared interests or values, rather than economic necessity. This could lead to a more diverse and interconnected society, with people free to explore new forms of social organization. Religion and spirituality could be influenced by these changes. As humanity's capabilities expand, our understanding of our place in the universe might shift, leading to new interpretations of spirituality and the purpose of life. This could result in a more global or even cosmic perspective on spiritual matters. Energy abundance could also impact global security. With fewer resources to fight over, conflicts might decrease, leading to a more peaceful world. However, the power of the Dyson Sphere could also become a point of contention, requiring careful management to prevent its misuse. The psychological impact of living in a world with unlimited energy could be significant. People might experience a greater sense of security and possibility, but they could also struggle with the existential implications of such power. Society would need to adapt to these new realities, finding balance and meaning in an era of abundance. Overall, the societal transformations brought about by a Dyson Sphere would likely be as vast and complex as the energy source itself. These changes could lead to a more equitable, creative, and peaceful world, but they would also present challenges that require careful thought, governance, and adaptation. The construction of a Dyson Sphere presents numerous technical challenges, each requiring innovative solutions. The sheer scale of the project is one of the most significant hurdles, as building a structure to encompass an entire star involves logistics on a level humanity has never attempted before. Coordinating the assembly of countless components across such a vast distance will require advanced automation and precise engineering. Material selection is another critical challenge. The materials used must be both lightweight and incredibly strong to withstand the forces exerted by the star's gravity and the structural stresses of the sphere itself. Developing these materials may involve breakthroughs in nanotechnology or the discovery of new exotic substances. Energy management during construction is also a major concern. Assembling a Dyson Sphere close to a star means dealing with extreme temperatures and radiation. The construction equipment and robotics must be designed to operate efficiently in this harsh environment, possibly requiring significant advancements in heat-resistant technologies. The transportation of materials to the construction site poses another challenge. Given the immense distances involved, moving the necessary resources from planets, moons, or asteroids will demand highly efficient propulsion systems and careful logistical planning. Each step of transportation must be optimized to minimize energy consumption and time. The coordination of autonomous robots and AI in the construction process will be crucial. These systems must work together seamlessly to build the Dyson Sphere, adjusting in real time to any changes or obstacles encountered. This requires sophisticated AI capable of managing a project of unprecedented complexity. Maintaining structural integrity during assembly is another technical challenge. As the sphere grows, each new segment must be carefully aligned and connected to ensure the overall stability of the structure. Small errors in alignment or positioning could lead to catastrophic failures, so precision is paramount. Communication across the construction site will need to be constant and reliable. With such a large area to cover, ensuring that all parts of the project are synchronized requires advanced communication networks capable of operating effectively, even in the presence of intense solar radiation. The risk of micrometeoroid impacts is a constant threat during construction. These small, fast-moving objects could cause significant damage to the structure or equipment if not properly managed. Protective shielding and real-time tracking systems will be essential to mitigate this risk. Scaling the construction process is another significant hurdle. The Dyson Sphere will need to be built in stages, each one carefully planned to integrate with the existing structure. This requires a modular approach, where each section can be assembled independently before being connected to the whole. Repair and maintenance during construction must be considered as well. Given the scale and complexity of the project, it's inevitable that some parts will need repair or adjustment as work progresses. Developing systems that can quickly and efficiently address these issues without delaying the overall timeline will be critical. Dealing with the star's variable activity is another challenge. Solar flares, radiation bursts, and other stellar phenomena can pose serious risks to both the construction process and the completed structure. The sphere must be designed to withstand these events, and the construction process must account for them as well. Powering the construction equipment presents its own set of challenges. While the star itself provides a vast energy source, harnessing and distributing that energy efficiently to power machinery across the Dyson Sphere will require innovative solutions, possibly involving wireless energy transmission or localized energy harvesting. Environmental control within the construction zone is also critical. As segments of the Dyson Sphere are completed, they will need to maintain a stable environment within, protecting equipment and future inhabitants from the star's intense heat and radiation. Designing these systems will be a complex engineering task. Finally, the sheer timescale of the project presents a unique challenge. Building a Dyson Sphere could take decades or even centuries, requiring a commitment to long-term planning and sustainability. Maintaining consistency and momentum over such a long period will require robust project management and the ability to adapt to new challenges as they arise. In summary, the technical challenges of constructing a Dyson Sphere are as immense as the structure itself. Overcoming these obstacles will require unprecedented innovation, coordination, and perseverance. But the potential rewards make the effort one of the most ambitious endeavors humanity could ever undertake. Only give me the words to be said by the voice actor. Do not provide any words other than the script. Do not number the lines or add quotation marks. This is a continuation of the script above. Don't use repetitive sentence constructs compared to the responses above. Write 2-3 sentences per paragraph. Ensure not to use the same paragraph phrasing as the sections above, and don't have a conclusion at the end of this segment as it will be continuing on to another segment. Write 15 paragraphs for this part. Financial costs and resource allocation. The risks of cosmic events, such as supernovae and gamma-ray bursts, pose significant threats to the construction and longevity of a Dyson Sphere. These catastrophic events could release immense amounts of energy, capable of devastating any structures within their range. Understanding and mitigating these risks is crucial for the survival of the Dyson Sphere and the civilizations it supports. A supernova, the explosive death of a star, could occur in proximity to the Dyson Sphere's star or in a nearby system. The intense radiation and shockwaves from such an explosion could damage or destroy large sections of the sphere, making it essential to monitor neighboring stars for signs of instability. Early detection and the ability to fortify or evacuate portions of the structure might be necessary to protect it from destruction. Gamma-ray bursts, which are among the most powerful events in the universe, emit incredibly high levels of radiation that could penetrate the Dyson Sphere and cause catastrophic damage. These bursts are difficult to predict and could originate from distant galaxies, yet still impact the sphere. Shielding the structure against such powerful radiation would require advanced materials and possibly the ability to temporarily power down sensitive systems to minimize damage. Cosmic rays, another form of high-energy radiation, could also pose a long-term threat to the Dyson Sphere's infrastructure. Over time, exposure to these particles could weaken materials, leading to structural degradation. Continuous monitoring and maintenance would be necessary to ensure the sphere remains intact and functional despite this constant bombardment. The gravitational effects of nearby cosmic events could also disrupt the Dyson Sphere's orbit or structural integrity. A close encounter with a massive object, such as a rogue planet or black hole, could exert powerful gravitational forces that might distort or displace sections of the sphere. Planning for these contingencies would involve precise calculations and possibly the development of thrusters or other mechanisms to stabilize the structure. Cosmic collisions, such as impacts from large asteroids or comets, present another significant risk. Even a relatively small object traveling at high velocity could cause severe damage to the Dyson Sphere. Advanced detection systems and defensive measures, such as deflecting or breaking up incoming objects, would be critical to protecting the structure from such impacts. The potential for nearby stars to evolve into red giants could also affect the Dyson Sphere. As these stars expand, they could alter the gravitational balance in the region, or even threaten to engulf parts of the sphere. Monitoring the life cycles of nearby stars would be essential for anticipating these changes and adapting the sphere's structure accordingly. Solar flares and coronal mass ejections from the Dyson Sphere's own star could also pose risks. These powerful bursts of solar energy could disrupt the sphere's systems, damage electronics, or even cause parts of the structure to overheat. Developing robust shielding and cooling systems would be vital to protect the sphere from these solar phenomena. The long-term stability of the star around which the Dyson Sphere is constructed must also be considered. If the star begins to show signs of instability, such as increased solar activity or unexpected changes in its life cycle, the entire structure could be at risk. Ongoing stellar monitoring would be essential for early detection of such changes, allowing for necessary adjustments or evacuations. Radiation from cosmic sources, including background radiation from the universe itself, could accumulate over time, leading to potential health risks for any inhabitants of the Dyson Sphere. Protecting the structure with radiation shielding and maintaining safe environments for living areas would be critical to ensuring the long-term viability of the sphere as a habitat. Magnetars, a type of neutron star with an extremely powerful magnetic field, could also pose a risk if one were to pass nearby. The intense magnetic fields generated by these objects could disrupt the Dyson Sphere systems, affecting everything from power generation to communication. Preparing for such rare but devastating encounters would require specialized protective measures. Galactic phenomena, such as passing through dense interstellar clouds or regions of high cosmic dust concentration, could impact the Dyson Sphere's operation and maintenance. These clouds could obscure light from the star, reducing energy collection, or deposit dust and debris on the structure, necessitating frequent cleaning and maintenance. The threat of a rogue black hole passing through the region poses another extreme risk. The gravitational forces and radiation from such an object could severely damage or even destroy parts of the Dyson Sphere. Although unlikely, this possibility would need to be considered in long-term risk assessments and disaster planning. Finally, the potential for unknown cosmic events, those that have not yet been observed or fully understood, adds an element of unpredictability to the risks faced by a Dyson Sphere. As humanity's knowledge of the universe expands, so too will our ability to anticipate and mitigate these risks. But the inherent unpredictability of the cosmos remains a challenge. In conclusion, the risks posed by cosmic events highlight the need for robust protective measures, advanced monitoring systems, and contingency planning to ensure the Dyson Sphere's survival in an unpredictable and often hostile universe. These risks must be addressed as part of the design and operation of the sphere to safeguard its long-term viability. Space debris poses a constant threat to the Dyson Sphere, given its massive surface area and exposure to the vastness of space. Even small particles traveling at high velocities can cause significant damage, puncturing the structure or damaging critical systems. This makes the management of space debris a top priority for maintaining the sphere's integrity. The accumulation of debris in orbit around the star could increase over time, exacerbated by the sphere's own construction and operation. Left unchecked, this debris could form dense clouds, creating a hazardous environment for both the Dyson Sphere and any spacecraft operating nearby. Effective debris tracking and mitigation strategies are essential. One of the main challenges is detecting debris early enough to avoid collisions. High-speed objects can be difficult to track, especially if they are small. Advanced radar and laser detection systems will be necessary to monitor the space around the sphere continuously, identifying potential threats in real time. Once detected, debris must be deflected or destroyed before it can impact the Dyson Sphere. This could involve deploying laser systems capable of vaporizing smaller particles or using kinetic impactors to nudge larger objects off course. These defensive measures must be reliable and quick to respond to any threats. Another approach to managing space debris is the creation of protective barriers or shields around vulnerable parts of the Dyson Sphere. These could absorb or deflect incoming objects, minimizing the risk of damage. However, such shields would need to be lightweight and durable, adding another layer of complexity to the sphere's design. The constant bombardment of microdebris, too small to track individually, presents a more insidious threat. Over time, this microdebris can erode surfaces, degrade materials, and wear down the sphere's protective layers. Developing materials that can withstand this gradual abrasion is critical to the long-term maintenance of the structure. Space debris from the construction process itself must also be managed carefully. With so many components being assembled in orbit, there's a risk that construction waste could contribute to the debris problem. Strict protocols for debris containment and disposal during construction would help mitigate this risk. The risk of chain reactions, where a collision generates more debris that then causes further collisions, is a serious concern. This scenario, known as the Kessler syndrome, could rapidly escalate, creating an environment filled with high-velocity debris. Preventing such a cascade is crucial for the Dyson Sphere's survival. International cooperation may be necessary to address the broader issue of space debris, especially if the Dyson Sphere is located in a system that shares space with other nations or entities. Collaborative efforts could include joint debris removal missions and the sharing of tracking data to reduce the overall threat level. Artificial debris such as derelict satellites or spent rocket stages represents another significant hazard. These larger objects can cause catastrophic damage if they collide with the Dyson Sphere. Efforts to remove or repurpose such debris should be prioritized, ensuring they do not become long-term threats. Maintenance operations will also need to factor in the constant presence of space debris. Repairing damage from impacts will be a regular task, requiring a fleet of repair bots capable of quickly addressing any breaches or malfunctions caused by debris strikes. These operations must be highly efficient to prevent minor damage from escalating. Designing the Dyson Sphere with redundancy in mind can help mitigate the impact of debris strikes. By ensuring that critical systems have backups and that the structure can remain operational even if part of it is damaged, the sphere's overall resilience can be improved. This redundancy will be vital in maintaining continuous operation. There's also the possibility of implementing active debris removal systems, which could continuously clean the area around the Dyson Sphere. These systems might include robotic arms, nets, or other devices designed to capture and dispose of debris before it can pose a threat. Ongoing research into these technologies will be essential. The impact of space debris on the energy-collecting systems of the Dyson Sphere could be particularly damaging. Even small particles could impair the efficiency of solar panels or other energy-harvesting components, leading to a reduction in power output. Protecting these systems from debris is therefore a top priority. In conclusion, the threat from space debris is a complex and ever-present challenge for the Dyson Sphere. Addressing it requires a multifaceted approach, combining advanced detection, active defenses, and ongoing maintenance. Only through careful planning and continuous vigilance can the sphere be protected from the dangers posed by the debris-filled environment of space. The construction of a Dyson Sphere carries significant socio-political and economic risks that could shape the future of global relations. The sheer scale of the project would require unprecedented levels of international cooperation, but it could also lead to intense competition for resources and technological dominance. Managing these dynamics will be crucial to preventing conflict. One major risk is the potential for economic disparity. The countries or corporations that gain control of the Dyson Sphere's resources could amass tremendous wealth and power, leading to global imbalances. This concentration of power could exacerbate existing inequalities and create new tensions between nations. The geopolitical landscape could also be transformed by the Dyson Sphere. Nations might align or realign their alliances based on access to the energy and resources the sphere provides. This shift could lead to new power blocks, increasing the complexity of international diplomacy and potentially heightening tensions. Economic instability is another concern. The introduction of virtually limitless energy could disrupt global markets, particularly those centered around fossil fuels or other traditional energy sources. Entire industries might collapse, leading to widespread unemployment and economic upheaval. The governance of the Dyson Sphere itself presents significant challenges. Deciding who controls the sphere, how its resources are distributed, and what laws govern its operation will require complex negotiations. The potential for corruption, mismanagement, or authoritarian control is a serious risk that must be carefully mitigated. Security concerns will also be paramount. The Dyson Sphere could become a target for sabotage, espionage, or even armed conflict, as various entities vie for control or seek to prevent others from gaining an advantage. Protecting the sphere from such threats will require robust defense mechanisms and international agreements. The risk of technological monopoly is another issue. If a single entity, whether a nation or a corporation, develops and controls the technology to build and maintain the Dyson Sphere, it could dominate global affairs. This could stifle innovation and create a monopoly on energy, with profound implications for global freedom and development. Public perception and social unrest could also play a significant role. The vast resources allocated to the Dyson Sphere might be seen as wasteful or unjust, particularly if people feel that more immediate concerns such as poverty or climate change are being neglected. This could lead to protests, political movements, or even revolutions. The environmental impact of constructing the Dyson Sphere could become a major point of contention. The extraction of resources from Earth or other celestial bodies could lead to ecological damage, sparking opposition from environmental groups and concerned citizens. Balancing development with environmental stewardship will be essential. Ethical considerations about the use and distribution of the sphere's energy could lead to moral debates and conflicts. Questions about who benefits from the energy, how it is used, and whether it is right to manipulate a star in this way could divide societies and influence policy decisions on a global scale. The potential for economic exploitation is another risk. Developing countries might find themselves at a disadvantage, unable to compete with or access the Dyson Sphere's resources. This could lead to new forms of colonialism, where powerful nations exert control over weaker ones through access to energy. The scale of investment required for the Dyson Sphere could lead to debt crises or financial strain on the countries involved. If the project were to fail or not deliver the expected returns, the economic consequences could be devastating, leading to long-term financial instability. Social cohesion within nations might be threatened as well. The concentration of wealth and power in the hands of those controlling the Dyson Sphere could lead to internal divisions, as people demand more equitable distribution of resources. This could exacerbate class tensions and lead to political instability. Cultural shifts might also result from the Dyson Sphere's construction and operation. The energy it provides could alter lifestyles, work patterns, and social norms, leading to unforeseen social consequences. Managing these changes will require careful attention to the cultural impacts of such a massive project. Finally, the long-term sustainability of the Dyson Sphere must be considered. If the sphere fails or becomes obsolete, the societies and economies that have grown dependent on it could face collapse. Ensuring the sphere's durability and planning for its eventual decommissioning are crucial to mitigating these long-term risks. In this comprehensive exploration, we've delved deep into the concept of a Dyson Sphere, a megastructure that could revolutionize humanity's energy consumption by harnessing the power of an entire star. We began by examining the basic principles of the Dyson Sphere, understanding its immense potential to generate virtually unlimited energy and the profound impact it could have on our civilization. We explored the various structural designs that could be implemented, from the classic Dyson shell to alternative concepts like Dyson swarms and Dyson bubbles. Each design offers unique advantages and challenges, showing the diversity of approaches that could be taken to achieve this ambitious goal. The discussion then moved on to the astronomical scale of resources and materials required for such a project. We considered the technical and logistical challenges involved in mining, transporting, and assembling the vast quantities needed to construct a Dyson Sphere. It's clear that achieving this vision would require unprecedented advancements in technology and international cooperation. We also considered the role of artificial intelligence and automation in making the Dyson Sphere a reality. The complexities of managing such a massive project, from construction to maintenance, would be beyond human capabilities alone, making AI and robotics essential to its success. The potential risks and challenges were also covered in depth, including the threats posed by cosmic events like supernovae and gamma-ray bursts, as well as the dangers of space debris. These hazards underscore the need for robust protective measures and contingency planning to safeguard the Dyson Sphere over its long operational life. We didn't shy away from discussing the socio-political and economic implications of constructing a Dyson Sphere. The project's sheer scale could reshape global power dynamics, influence international relations, and raise significant ethical questions about resource allocation and the potential for inequality. In addition to the Dyson Sphere itself, we explored alternative energy megastructures, considering other ways humanity could harness the power of space. Concepts like the Matryoshka brain, space-based solar power stations, and orbital rings offer diverse possibilities for the future of energy. Speculative future scenarios were also a key part of our discussion. We imagined the profound changes a Dyson Sphere could bring, from enabling interstellar exploration to creating post-scarcity societies, and even the potential risks of complacency or inequality. These scenarios highlight both the promise and peril of such an ambitious project. Finally, we examined the feasibility of constructing a Dyson Sphere within the next century. While the challenges are immense, the rapid pace of technological advancement offers hope that humanity could one day achieve this incredible feat, setting the stage for a new era of energy abundance and exploration. If you enjoyed this deep dive into the Dyson Sphere and the future of energy, please remember to like this video and subscribe to our channel. We have many more videos exploring fascinating topics in science, technology, and the future of humanity, so be sure to check those out as well. Thank you for watching, and we look forward to seeing you in the next video.